Thank you, Professor Aniruddha Poria, to participate in this conference. Professor Aniruddha will speak about the heat semigroup associated with the Jacobi-Cherednik operator and its application. Please go ahead.
Thank you. First, I want to thank organizer for giving me the opportunity to talk here. So, in this talk, I will discuss heat semigroup associated with Jacobi-Chernigg operator and some of its application. So, here is the outline of my talk. First, I will discuss different differential difference operator, and then in particular, I will discuss Jacobi-Chernigg operator, and then we will mention the square of the Jacobi-Chernigg operator and study Jacobi-Chernigg heat kernel and heat semigroup. Then, as an application, I will discuss some problem on probability theory and discuss about Jacobi-Chernigg process and solve modified Poisson equation. First, I will start with the Dunkel operator. So for some parameter alpha is greater than equal to minus half, the Dunkel operator acting on some smooth function f on R is defined by d alpha f, which have the following expression. This Dunkel operator extended to the Jacobi-Dunkel differential difference operator by Jacobi, which is defined using the parameter alpha, which is bigger than minus half, and beta is a real number. Then Jacobi-Dunkel differential difference operator is defined on R, which have the following expression. And if we observe that these two operators have the similar form, both of these operators can be written using the operator delta x. Here, if we can see that if we take A as some hyperbolic function sine and cosine, then we can get the Jacobi-Dunkel operator from the operator delta. And if we take ax is x square power alpha plus half, then we can get the Dunkel operator. And these two operators are well defined for f is in C1R, and both have the singularity of the form a dash x by x of the form 2 alpha plus 1 by x at the point x is 0. So here mainly we will consider the Jacobi-Chernigg differential difference operator T alpha beta, which is defined on R by T alpha beta fx is delta fx, which is Jacobi-Dunkel operator, minus rho f minus x. Here the parameter alpha and beta satisfying the that alpha greater than equal to beta greater than minus half, and alpha is bigger than minus half, and rho is alpha plus beta plus 1. So here we'll study the square of this operator T alpha beta. And mainly here we'll show that the heat equation associated with the Jacobi-Chernigg operator as a solution from alpha beta T fx is integral over R small p alpha beta T xy fy a alpha beta y dy. So here this p alpha beta T xy is the heat kernel, which is strictly positive. Also, we prove that the heat semigroup P alpha beta T is bigger than or equal to 0 is strongly continuous semigroup of operator on the space L2R A alpha beta. So this space consisting of square integral function on R with respect to the measure A alpha beta x dx. Also, using the Obdam-Chernigg transform and the structure of semigroup, we will discuss a spectral representation of heat kernel P alpha beta T, which have the following form, where this G alpha beta lambda is the eigenfunction of the Jacobi-Chernigg operator T alpha beta lambda, and D sigma alpha beta is the generalized tangential measure. So as an application, we solve the modified Poisson equation for all f is in L1, and from there, from the semigroup P alpha beta T bigger than or equal to 0, we obtain a new family of Markov process xt is bigger than or equal to 0 on the real line, which we call the Jacobi-Chernigg process with transition probability densities given by P alpha beta T xy, A alpha beta y. Also, we show that the absolute value mod xt is bigger than equal to 0 of the Jacobi chaining process is diffusion process with the infinite Samuel generator of this form. So first I will start with the definition of Jacobi chaining operator. Then from there we will define the Jacobi chaining transform. So first, this T alpha beta denotes the Jacobi chaining operator, which also is called the Dunkel chaining operator, which have the following form, where the parameter alpha beta is given by alpha greater than equal to beta greater than equal to minus half and alpha greater than minus half. And rho is alpha plus beta plus 1. So we can write this T alpha beta in the closed form, where this A alpha beta x is sine hyperbolic mod x power 2 alpha plus 1 cos hyperbolic x power 2 beta plus 1. So here we define the Opdam hypergeometric function, which are the eigenfunction of the operator T alpha beta with the eigenvalue I lambda, and which is all normalized such that G alpha beta 0 is 1. And using this G alpha beta lambda, we will define the Jacobi chaining transform. So first we will define the eigenfunction G alpha beta lambda using the hypergeometric function. So G alpha beta lambda we can write in terms of hypergeometric function phi lambda alpha beta, and where this phi alpha beta lambda is 2f1, which is a hypergeometric function. So here I want to mention that for any lambda in R, G alpha beta lambda is a real and strictly positive. So now we'll mention some properties of the hypergeometric function G alpha beta lambda. We have the following estimate for the derivative of G alpha beta lambda. And this G alpha beta 0 for lambda is 0 is strictly positive, and it is bounded by C 1 plus x or minus 2x if x is bigger than equal to 0, and C if or rho x if x is less than equal to 0. For any lambda in R and x in R, we have this G alpha beta x is bounded by G alpha beta 0x. This hypergeometric function G alpha beta lambda have the property that G alpha beta lambda dx is G alpha beta lambda dx for every lambda in C and x and t in R. In particular, if you take t is 0, then G alpha beta 0 is same as G alpha beta lambda 0, which is 1. Now, let us take CCR with a base of continuous function on R with complex support. Then Opdam chaining transform is a Fourier transform in the trigonometric Dunkel setting, which is defined by the G H alpha beta f lambda. The Opdam chaining G alpha beta f of a function f is in CCR is defined by H alpha beta f lambda is integral over R fx. Then G alpha beta lambda minus x. Then we have the measure A alpha beta x dx. The inverse Opdam chaining transform is defined on some suitable function on R, such that H alpha beta inverse gx is integral over R G lambda, then G alpha beta lambda x, then D sigma alpha beta lambda. And this D sigma alpha beta lambda is the measure defined by this expression, where this C alpha beta lambda we call the Christian function. We also have the Planck formula like the Fourier transform for the Opdam chaining transform. The Planck formula is given by the following expression. Here we denote the LPR alpha beta or LPR sigma alpha beta. The LP space corresponding to the measure T alpha beta x and D sigma mod alpha beta x. So first I will define two Schwarz space. So first one is the S alpha beta R. This is defined by cos hyperbolic x power minus rho SR is defined the space of all tempered distribution F such that we have this is finite and which is equipped with the obvious seminum. And Opdam chaining transform and its inverse are the topological isomorphism between the Schwarz space S alpha beta R and the usual Schwarz space SR. Again, here I will mention two Schwarz space. First is the weighted Schwarz space. So S R alpha beta R is the weighted Schwarz space, which is defined by cos hyperbolic x power minus rho by R SR equipped with the topology given by the seminum. And Another Schwarz space is omega epsilon r with the extended Schwarz space of all function A's that are analytic in the interior of omega epsilon r, which is defined by G in C, such that image of G is less than epsilon r, where epsilon r is 1 by r minus 1 rho, such that is together with all its derivative extended to continuously to omega epsilon r and satisfying this is finite. Now we can see that for r is 1, this S omega epsilon r is the usual Schwarz space SR. For all r in between 0 to 1, the Obdam-Chainik transform is the topological isomorphism between SR alpha beta and S omega r. Also, the Obdam-Chainik transform extend uniquely to a isomorphism from L to R alpha beta to L to R sigma alpha beta. So here we already discussed that H alpha beta lambda are the eigenfunction of the operator T alpha beta with eigenvalue I lambda. Then using straightforward calculation, we can see that this T square alpha beta G alpha beta lambda is minus lambda square G alpha beta lambda x. That means T alpha beta lambda are the eigenfunction of the operator T alpha beta square with eigenvalue minus lambda square. So here we will study the T alpha beta square. First, I will show the expression of T alpha beta square. If we consider the operator dfx is the derivative of f, and mfx is fx minus f minus x by 2, and sfx is f minus x. And using the fact that for f is in C2, using the fact that E alpha beta dash by E alpha beta is an odd function, we can get the expression for T alpha beta square. So here we will consider a subspace of C2 consists of all functions satisfying the derivative of f at the point x0 plus rho square fx0 less than or equal to 0 if this derivative of f, second order derivative at the point x0 is less than or equal to 0. Some point x0, we denote the space C2 rho r and show that C2 rho r is non-empty. So here, if we consider the Gaussian function and take the parameter alpha is half and beta is minus half, then we can see that for this function satisfying these properties, so that this space C2 rho r is non-empty. So also here we observe that if we take f is from weighted Schwarz space and lambda in R, then H alpha beta T alpha beta square f lambda is minus lambda square H alpha beta f lambda. Here first proposition says that if omega subset of R be open and symmetric, if a real valued function f is in C2 rho r at an absolute maximum at the point x0, that is fx0 is supremum s belongs to omega fx, then T alpha plus fx0 is less than or equal to 0. Here I will skip the proof of this proposition and define the Hagman-Obdam Laplacian d alpha beta is defined by d alpha beta is d alpha beta square minus rho square. And then Jacobi-Chernigg heat operator is defined by h, which is this partial derivative at t minus 0 alpha beta on C2 omega cross 0t, where omega subset of R is open and t is positive. Let CB denote the case of all continuous and bounded function on R. We consider the homogeneous Cauchy problem for a given f in CBR. Find U belongs to C2 R cross 0t intersection C R cross 0t such that HU is 0 on R cross 0 and U dot comma 0 is F. So here I will first define the function using the inverse of the Chernigg transform, and we call it as the fundamental solution of the Jacobi-Chernigg heat equation. So here this fundamental solution f alpha beta t is defined using the inverse of the Chernigg transform of the Gaussian point rho square. So then we have shown that for every t is positive, the function f alpha beta t is in weighted Schwarz space for every r in between 0 to 1. Also, the function from xt to f alpha beta tx is infinitely continuously differentiable on r cross 0 infinity and is solution of ag is equal to 0. So again, I will skip the proof of the proposition 2 and we'll continue. So for xy in R and t bigger than 0, we define the heat kernel using the generalized Jacobi-Chernigg translation and the fundamental solution of the Jacobi-Chernigg heat equation. So for x in R and f is in weighted source space, the generalized translation operator is defined T alpha beta x at the point fy is defined by this integral, where we have used the Obdam-Chernigg transform and the hypergeometric function and the measure, Banchel measure. So then using this generalized translation, we define the Jacobi-Chernigg heat kernel T alpha beta Txy is T alpha beta minus x F alpha beta Ty. So here we first mention some properties of the heat kernel. So for xy in R and t bigger than 0, we have the following expression for the Jacobi-Chernigg heat kernel. Also, for all x in R and t bigger than 0, P alpha beta Tx0 is F alpha beta Tx. And for all xy in R and t bigger than 0, P alpha beta Txy is P alpha beta T minus y minus x. So also we have this P alpha beta T x dot belongs to the weighted source space, and if we apply the Obdam-Chernigg transform on the heat kernel, then we get the e power minus t by 2 lambda square plus into T alpha beta Tx. We have the following properties that integral over R T alpha beta Txy T alpha beta y dy is e power minus t by 2 rho square. For fixed y, the function uxt is P alpha Txy solves the Jacobi-Chernigg heat equation is u equal to 0 on R cross 0 infinity. Again, I will skip the proof of this proposition. So next I will define the heat semigroup using the heat kernel. For f is in weighted source space and t bigger than equal to 0. We define the Jacobi-Chernigg heat semigroup E alpha beta t bigger than equal to 0 by the following integral over R P alpha Txy Fy E alpha beta dy if t bigger than 0 and is fx if t is 0. So from the part D of the provision 3, we have this P alpha Tx is in L1 R I alpha beta or is t bigger than 0. Since f is bounded, this P alpha T is well defined and continuous on R. So here first theorem says that if f is in weighted source space and the function uxt is P alpha Tfx on R cross 0 infinity, solves the Cauchy problem. Also, this heat semigroup P alpha T satisfies the following properties that P alpha Tf is in weighted source space for which t bigger than 0, and P alpha beta T plus SF is P alpha beta T, P alpha beta SF for every S and T bigger than equal. Also, P alpha beta Tf minus F, this infinity norm is goes to 0 if T is goes to 0. So again, we will skip the proof of this theorem, and here we show that the linear operator P alpha T bigger than equal to 0 on SR alpha beta R extend to a positive contraction semigroup on a subspace of Banach space C0R infinity, where C0 is the base of continuous function on R vanishing at infinity. So this is the main theorem of this talk. So first I will mention the statement and I will give some idea of the proof of this theorem. Let C0R be a subspace of C0R consist of functions at 7. Then we have the following properties. Operator T alpha beta square on C0R is closable and its closure generates a positive strongly continuous contraction semigroup on C0R.
Excuse me, Professor. Excuse me, Professor Poria, can you already, your time is on, is...
Okay. So can you give me 2 minutes to conclude the talk? Or
yes, please. Can you give your conclusions?
Okay, fine. So then here we have shown that this heat kernel P alpha beta T is non-negative on R cross R, And the X and P alpha T closure on C0 is given by this integral. So the idea of this proof is that here we have used the Helly's, Yoshida, and Phillips theorem to prove this theorem. So I will skip the proof, and in the next result we have shown that this Jacobian heat kernel is strictly positive on R cross R. Okay, so since we don't have enough time, so I will stop here. Again, I want to thank organizer for giving me opportunity to present my work here. If you have any questions, please ask.
Thank you, Professor Poria. I have a question.
Yeah.
What is the motivation of to study this equation? I think I skipped this.
Okay. So this motivation started from the Dunkel operator. So this differential difference operator are started from the Dunkel operator. Then it's generalized to the Jacobi-Dunkel operator. So here we have considered this Jacobi-Chladni differential difference operator, and we started from there and considered the square of this operator, and from there we have defined the heat kernel and heat semigroup. And our motivation is to use this heat kernel and heat semigroup to solve the modified Poisson equation. And using that, we want to apply in the probability theory. And using this operator, we solve some application of the.
Okay.
This part I already not mentioned. Yeah, application of this part I have not mentioned.
Are there any other question? Well, we thank Professor Poria for his participation. Thank you.
Okay, thank you.
The next speaker is Professor Nikhil Khanna.
Yes, Professor Juan, I'm here.
Okay, and Professor Nikhil Khanna will speak about a note on periodicity wavelet packets. Please go ahead.
First of all, I would like to thank all the organizers. Special thanks to Professor Xavier and Professor Juan for organizing the 4th edition of this online conference. This is, in fact, a very good opportunity for mathematicians all over the world. And now I've been seeing this thing for a long time now. Participants from various countries are involving in this discussion and this conference. Thanks once again. So the title of my talk is A Note on Periodized Wavelet Packets. And this is the overview of my talk. So we will start with the introduction, where we will study some of the basic concepts of wavelet theory, and followed by periodized wavelet packets. There's a new concept which we have defined as generalization of periodized wavelets. And finally, as an application, we study some of the approximation properties and related to errors of the subspaces involved in this theory. So let us just start with the introduction. So in 1988-89, the concept of multi-resolution analysis was introduced by Malat and Meyer. And this actually led to the construction of wavelets and their generalizations. So these are the two monumental papers by Malat and Meyer, published in the year 1989. So let us just look at the definition of multi-resolution analysis. So as a short form, we call it as MRA. So MRA is defined as an increasing sequence of closed subspaces, Vj, of L2R satisfying these 5 properties. The first property is that Vj is subspace of Vj plus 1 for all j belongs to Z. Second, second is an biconditional statement which says that if f belongs to Vj, then the dilated version of f belongs to Vj plus 1 and vice versa for all j belongs to set of integers. The third property says that the intersection of all these subspaces is a singleton set 0. The fourth one is that the closure of the union of these spaces is equal to the L square space, L2 space. And the fifth property says that, which is actually the most important property because which talks about the building block of the wavelet theory, that is the scaling function phi, that it says that there exists a function phi belongs to V naught such that the set of the translated versions of phi where k belongs to Z is an orthonormal basis for the function phi, whose existence is given in the part 5, is called a scaling function of the given MRA. The scaling function actually satisfies the given equation given by 1, that is also known as the dilation equation, that is phi x is equals to summation up phi of 2x minus p, with the condition that the zeroth vanishing moment, that the modulus of the zeroth vanishing moment is equal to 1. But it is always convenient to choose the phase of phi so that the integral is always equals to 1. So this means that it is not always required that the integral of the phi x function is 1. Also, the associated wavelet function is defined by a similar series where the coefficient Vp is a different coefficient. In 1992, Koifman et al. They introduced the notion of wavelet packets to improve the frequency resolution of signals. Now, the question arises when we already have this concept of wavelets, so why they actually introduce this concept, which is the generalization of wavelets. So initially, if we talk about reconstructing a signal and to analyze the signal, we usually use Fourier transform. But the problem with the Fourier transform was the localization of the time and frequency information. So later it was corrected by short time Fourier transform, where you fix a time domain and then you just translate that domain over the interval and you can find the frequency for that specific time. Now, but it was very time consuming and it was expensive process. So they shifted to the concepts of wavelets. Now, what happened with the wavelets, that when you talk about the wavelets, you actually talk about the translated and dilated versions of the wavelets. And we found that there is a poor translation invariance and poor frequency. I mean, the dilation invariance happen because of the wavelets. And this was corrected by this new introduction, which was, long back in 1992, introduced by the team of Koifman and his friends, his colleagues. And this notion actually provided us with quick access to a rich library of orthonormal bases. And because of which, the best bases can also be selected. So the present paper actually is the initial work on the theory of wavelet packets. Although they have written few more papers during the same year, which are based on the wavelet packets, but this was the initial work. So let us just look at the definition of Dopshi's wavelet packets. This is actually the generalization of the definition of wavelet packets. So a family of functions omega n for n equals to 0, 1, 2, so on, to defined by these two expressions. So if we look at the first expression, it talks about omega 2n of x, which is equals to sum ranging from 0 to 2g minus 1, up omega n 2x minus p. And the another term is omega 2n plus 1 of x, which is summation which ranges from 0 to 2g minus 1, Vp omega n 2x minus p. Now, if you relate these two expressions, omega 2n and omega 2n plus x, and if you just substitute here n equals to 0 here and here, you will obtain omega 1 and omega naught, and which are respectively the psi and phi functions, which we have already defined in the previous slides. We have seen that there are two functions which are, having the similar expressions. Now we have already defined during the definition of multi-resolution analysis that phi function is known as a scaling function. The other name for the phi function is the father wavelet. So it's actually the father of the family, the building block of the family. And this family is known as Topshe's wavelet packets. Now let us just look at the wavelet packet decomposition. So let us just look at, so we have a signal Y and we apply the filters on Y, the filter H that is known as the low pass filter, and filter G that is the high pass filter to the signal Y, and then recursively to each intermediate signal, we can see that giving us the tree diagram of wavelet packet algorithm. So we can see that to every branch of it, to every branch, we have a filter. A filter is applied. Now, whereas in case of wavelet decomposition, you can see that the right-hand node is sprung. It's not available here, meaning that the lower level decompositions are not computed from the right-hand branches. So this means that the initial, the generalization of the wavelets, that is wavelet packets, this kind of decomposition of a signal at each node of the tree by the applications of two filters is actually known as a splitting algorithm, and it actually helps us in finding a best basis, because suppose you are given a signal and if you want to just find the decomposition of signal using these two branches, it's okay. Now suppose you want to decompose the same signal using this part of the signal, it is actually giving you a close eye to that signal. Actually, it works in like you are zooming in over some information. You can analyze the signal, you can analyze the data much better if you are using the wavelet packet decomposition. So the best basis algorithm, which was defined by Koifman and Wickerhauser, it consists of traveling down the tree structure. As we have seen that we are just traveling down the tree structure, making a database decision at each node as to whether we need it or we want to split it or we don't want to split it. So this result actually represents the best basis, as we have already discussed it. And it helps us to represent the particular set of data under process. Restrepo et al. Introduced periodized wavelets by restricting the wavelets on bounded subsets of R, which were used to examine the benefits and properties of wavelet projection techniques for differential operators. So, and this is the work of Restrepo, published in 1996 as a technical report. Later, Klepnecker observed that employing periodized wavelet packet transform, he talked about the generalization of the wavelet packets on quantum computer is much better and economical than the periodized wavelet transform. And this is the work by Klepnecker, published in the SPI proceedings in year 1999. Now, let us just try to understand the concept of periodized wavelet packets. So in general, the wavelet packets are defined on R. However, for many applications, wavelet packets defined on a periodic domain are needed. Interestingly, wavelet packets which are defined in general can be periodized with the technique of Poisson summation and give rise to periodic wavelet packets. So let us just look at the definition of Dobschi's periodized wavelet packets, which is different from the existing definitions of wavelet packets. So the wavelet packets omega n obtained from scaling function using multi-resolution analysis are said to be periodized in the sense of Dobschi's. So if it satisfies this condition, that if the periodized omega j and k of x can be expressed as the series L from minus infinity to infinity, omega j and k of x plus L, where j and k belongs to set of integers and x is a real number. And we have this very good remark regarding the periodized Dobschi's periodized wavelet packets. Like periodized wavelet packets, unlike the case of non-periodic ones, they must be first dilated before periodization, as periodization does not commute with dilation. So we have to be very careful while working with periodized wavelet packets. In the following result, we are giving some properties of the Dobschi's periodized wavelet packets. So let us just look at this theorem. So let omega n belongs to L square R be wavelet packets. Then for any j comma k belongs to Z, the periodized omega j and k is one periodic. Property number 2 says for j less than equals to -1 and k belongs to set of integers, s belongs to n naught and x belongs to R, the periodized omega j 4s plus 1 comma k is equals to 0. But for j equals to 0, the periodized omega j 4s plus 1 comma k of x is neither 0 nor any constant for odd choices of k. The third property says that for j greater than 0, the periodized omega j and k is periodic in the shift parameter with period 2 raised to power j. And the fourth one says for j greater than j prime greater than equal to ceiling function log 2 2g minus 1 and x belongs to close interval 0 comma 1 with omega n having compact support 0 comma close interval 0 comma 2g minus 1, the periodized omega j and k can be expressed as omega j and k of x if x belongs to ijk intersection close interval 0 comma 1, where ijk is actually this support of omega j and k, which is given by this close interval. Whereas it can be expressed as omega j and k of x plus 1 if x belongs to close interval 0 comma 1, but x does not belongs to the support of the omega j and omega n. The following result shows that the Dobschi's periodized wavelet packets form an orthonormal system for L square close interval 0 comma 1. So it says that the collection of periodized Dobschi's wavelet packets, this collection is an orthonormal system for L square of close interval 0 comma 1. And its corollary says for each fixed j belongs to capital Z, the collection of periodized Dobschi's wavelet packets forms an orthonormal system for L square close interval 0 comma 1. Now let us move to the approximation properties of the periodized subspaces Vj. The domain of periodized wavelet packets, when restricted to close interval 0 comma 1, generate an MRA of L square close interval 0 comma 1 analogously to that of L square R. So in the very initial section, we have learned about the MRA of L2R. The L2R space. And now since we are dealing with the periodized wavelet packets, so we are actually restricting its domain to 0 comma 1, close interval 0 comma 1. The significant subspaces involved are defined as periodized Vj, which is given by the span of these expressions, and periodized Ujn, which is given by the span of the expression periodized omega j and k of x, where x belongs to close interval 0 comma 1 and belongs to natural numbers, and k ranges from 0 to 2 raised to power j minus 1. Note that this periodized Vj they are nested similarly as in the case of non-periodic MRA. So this theory is refined analogously to the theory of the non-periodic MRA. So we can say that these are the things which we have studied in the definition of MRA also. And so this gives us that the closure of the union of the periodized Vj is equal to L square closed interval 0. And using the orthogonality relationships, we can express the L square of closed interval 0, 1 as the direct sum of periodized Vj1 and the direct sum of the another space that is periodized U0, n for some J1 greater than 0. Let F be member of the periodized Vj and let J1 be such that it satisfies this condition. And the periodized wavelet packet expansion, I mean the very important expansion which we have defined, can be expressed using the periodized omega J1 0, k and periodized omega 0 n, k for x belonging to closed interval 0, 1, where the coefficients Cjk and dn0k, they are respectively given by these two integrals. Let omega n be wavelet packets. Then the orthogonal projections of L square closed interval 0, 1 on the periodized Vj space and periodized U0, n spaces respectively are given by these two sums, where Cjk and dn0k are the respective integrals. And using that, we have this expression for the orthogonal projection on periodized Vj space. And this helps us actually, this result actually helps us to find the approximation error, which is given by fx minus the orthogonal projection on periodized Vj. And this is actually the application part, which is the result related to the approximation error, and which says that let f be a function belonging to L square closed interval 0, 1 and intersection Cg of R, where G is greater than 1, be a function such that it satisfy, along with the condition on omega n, that omega n be Dobschi's periodized wavelet packets, such that the modulus of omega n is of this order of 2 raised to power minus gj for n ranges from 2 raised to power j and 2 raised to power j plus 1 minus 1, where j is greater than or equals to 0. And secondly, that the vanishing moments are given where p ranges from 0 to g minus 1. Additional to these two conditions, if we assume that j belongs to the set of integers, such that j is greater than or equals to j1, which is greater than 0, where 2 raised to power j1 is greater than or equals to 2g minus 1, then the uniform norm of the periodized Ej of x is of this order, that is order of 2 raised to power minus j, g minus 1. So this is all about the application, and these are some of the references. Thank you very much.
Thank you, Professor Nikhil. Questions? I have a question.
Yeah, please.
The orthonormal basis that you find, is it associated with a differential operator like the one in seno and coseno? Are they associated with the differential operator, the basis you get?
No, they are not associated with the differential operators.
Okay. Thank you.
Thank you very much.
Are there any other questions? Okay, thank you, Professor Nikhil.
Thanks once again, Professor Juan, for giving this opportunity. Thank you very much.
The next speaker is, I hope I can speak it out good. Rushi Bargap. He's going to
Yes, sir.
speak dynamical sampling in quaternionic Hilbert spaces.
Good evening,
Please
Professor
go
John.
ahead.
Am I audible to you? Good
Please
evening,
go.
sir. Am I audible to you?
Please, you can start.
Yes, sir. Good evening, everyone. My name is Ruchi Bhardwaj, and the topic of my talk is dynamical sampling in quaternionic Hilbert spaces. So firstly, we'll have the introduction and some motivation. Then we'll have the required preliminaries. We'll discuss dynamical sampling firstly in finite dimensional quaternionic Hilbert spaces, and then dynamical sampling in infinite dimensional quaternionic Hilbert spaces, and then dynamical sampling for general bounded operators. So the idea of dynamical sampling is basically to ensure the recovery of an unknown function f, which is evolving in time through some operator t, from the roughly sampled states t and f at each time n. Now it basically deals with finding the sampling positions of t and f for each n that permits the reconstruction of the function f. The technique here is to repeatedly apply an operator to a function f to get its future states, and then they are again specially sampled at some given positions at each time level to recover the complete information about the initial state of that function. Here in this talk, we investigate the notion of dynamical sampling and some important results concerning dynamical sampling for quaternionic Hilbert spaces where commutativity is generally absent. Mathematically, for a quaternionic Hilbert space H and a bounded operator T acting iteratively on some f in H, the system under consideration is the sample system T, Tn Fm, where n belongs to omega m and m belongs to some index set j, and omega m is the set from 0, 1 to km, depending on the set index m. Now we need to find the necessary and sufficient conditions on this operator t and set omega m and j that can completely recover the function f from this sample system. In terms of frame theory, our problem here turns out to look for the conditions that allow the system T to form a complete system basis or a frame for a right quaternionic Hilbert space H. So throughout this presentation, H denotes a right quaternionic Hilbert space, and by R span we mean the span with scalars on the right hand side of the vectors. Sigma t and sigma pt denotes the spherical and spherical point spectrum respectively, and En denote the standard orthonormal basis of the space L2I, and I and J are index sets. Quaternions are basically a four-dimensional non-commutative extension of the complex numbers over R. The quaternionic algebra H contain elements of this form Q equals to Q naught plus I Q1 plus J Q2 plus K Q3, where Qn belongs to R and the units I, J, K satisfies the following inequality. For any Q in quaternion, its conjugate Q bar is given by this expression Q naught minus I Q1 minus J Q naught Q2 minus K Q3. And this directs a norm of Q in H defined as the modulus of Q equals to square root of Q into Q bar. Also, for any non-zero quaternion Q in H, there exists a Q inverse in H defined by the following equation. Next, we have the definition of a right quaternionic vector space. It is a linear vector space with the right multiplication of scalars from the skew field H, That is, there exists a mapping from H cross quaternions to H, which satisfies the following three properties, similar to somehow a vector space. Next, a right quaternionic inner product space is basically a right quaternionic vector space endowed with an inner product from H cross H to the space of quaternions that satisfies the following four properties of linearity and conjugate symmetry and so on, and how the scalars come out in this inner product. And if this right quaternionic pre-Hilbert space is complete with respect to this norm induced by the above defined inner product, then we say it is a right quaternionic Hilbert space. This is an example of a right quaternionic Hilbert space which we are going to use often. It is a space of the square summable quaternionic valued sequences given by this set L2I under the right multiplication by quaternions, together with this inner product given by the following equation. It forms a right quaternionic Hilbert space. Now we discuss frames in quaternionic Hilbert spaces. We say a sequence Fn in H is a frame for H if there exist two positive constants R1 and R2 satisfying the following inequality, which we are calling as a frame inequality. The constants R1 and R2 are referred as lower and upper frame bounds of the frame respectively, and the sequence Fn, if it only satisfies the upper frame condition, then it is known as a Bessel sequence for H. And if it is known as a redundant frame, if it is not a Riesz basis, it properly contains a Riesz basis. Now we define a frame operator for a given Bessel sequence. For a given Bessel sequence Fn in H, the operator T from the space L2I to H, defined like this, is known as the synthesis operator for the sequence Fn. And its adjoint operator Tf star from H to L2I, given by this equation, is known as the analysis operator. And by composing these two operators, Tf and Tf star, we obtain the frame operator on H given by the following expression. Now, mathematically, the problem here is to recover the initial state of an evolving function f in L2I from the sample system T, which is of this set, taken at different time levels n, where j is an index set and omega is the given this set. Mathematically, we have this theorem which states that the system T can recover every f in L2I if and only if the corresponding system T star and EM, where ENs were the orthonormal bases of L2I, then this system forms a frame for L2I. Now, we discuss dynamical sampling firstly in finite dimensional quaternionic Hilbert spaces. Here, the index set I is the finite set from 1 to D, and the right quaternionic Hilbert space is this space HD. Consequently, the evolution operator T is a finite matrix acting on HD. We firstly consider the case when this matrix T is a Hermitian matrix, similar to some diagonal matrix D. Now, if Pk denotes the orthogonal projection of HD onto the right eigenspace kernel of D minus I gamma k corresponding to each gamma k, then we have the following expression for the operator D in terms of these orthogonal projections. Next, we give a characterization for the system to form a frame. We are saying let Pm be a given set of vectors in HD and Dm be the degree of D annihilator of each Pm. Then the following two statements are equivalent. The system D, which is given by the set D and Pm, where n varies from 0 to Dm minus 1 and m is in this set J. The system forms a frame for HD if and only if the PKPM, this set of projections of each vector PM, this forms a frame for range of PK, a range of the projection operator for each K. For this, we have an example where D is a Hermitian matrix acting on H2 and P1, P2 be two given vectors. It is easy to observe that H2 can be expressed as a direct sum of these two subspaces in the following form. And operator D can be written as the linear combination of these two orthogonal projection, P1 plus 2P2, where P1 and P2 denote the orthogonal projection onto the right subspace kernel of D minus I and kernel of D minus 2I respectively. Then this M1x and M2x are the D annihilators of P1 and P2 of degree 1. Therefore, D1 and D2 here are 1. Now we are saying that the orthogonal projection of these vectors P1 and P2 on the kernel of D minus I given by this following set clearly spans the right subspace kernel of D minus I. and hence it forms a frame for the range of P1 since we are in finite dimensional. Similarly, the orthogonal projection of P1 and P2 on the subspace kernel of D minus 2i, it forms a frame for range of P2. From this, we conclude that the system J0, 0, J, this forms a frame for H2. Now, usually the number of iterations dm, as we have taken in the previous theorem, corresponding to each pm depends on the index m. But in some cases, the number of iterations may be independent and even less than dm. And this is illustrated by the following result, in which we have let pm be a given set of vectors in HD, and pkpm forms a frame for a range of pk for each k. Then for a fixed m in n0, where n0 is n union the singleton 0 set, the following two statements are equivalent. The system D given by the following set, it forms a frame for HD if and only if this system D to the power m plus 1 of Pm, this is contained in the right linear span of the system D. Next, we again give a characterization for the system T to form a frame. Here we are taking T as a Hermitian matrix acting on HD and Pm be a given set of vectors in HD. We take Y as the right linear span of these vectors Pm. Now for any gamma in the spectrum of T, let K gamma be the complementary subspace corresponding to the range of T minus I gamma, such that HD can be expressed as the direct sum of these two subspaces, and pi K gamma denotes the projection onto the subspace K gamma along the range of T minus I gamma. Then the following statements are equivalent. First is the system T given by this set forms a frame for HD. Second is pi K gamma, that is the projection onto the subspace K gamma along range of T minus I gamma, maps the subspace Y onto K gamma, means this map is surjective. And thirdly, the orthogonal projection on the subspace kernel of T minus I gamma maps Y onto kernel of T minus I gamma. Nextly, dynamical sampling in infinite dimension. In this section, the index set under consideration is N0, and the objective again here is to find the conditions such that the system T, again given by this set T and Fm, where n is in omega m and m belongs to the index set J, it reconstructs every f in L2 N0, or equivalently, as we have done in the finite dimensional case, the mathematical formulation T star n em, this forms a frame for L2 N0, where T is a bounded operator. Firstly, we recall the definition of a diagonal operator. It says that an operator D on H is said to be a diagonal operator if there exists an orthonormal basis phi k of H and some scalars pk in the quaternionic scalars, such that D of phi k is equals to phi k pk for each k. Then this operator is a diagonal operator. Here we consider, in this section, we consider T to be a bounded self-adjoint operator and L2 and not have a basis consisting of the right eigenvectors of T. Now, firstly, for the case of finite index set J, if we consider J to be a finite index set, then we are saying that the system T, which is T and EM, this set never forms a minimal set in L2 and not if it is complete in L2 and not. And since it never forms a minimal set, it will not form a right basis also. Now, since the possibility of T being a minimal set or a basis is already ruled out for the case of a finite index set, we'll further prove in the following result that the system even forms a frame under some specific conditions only. If G is a finite index set, then the system T given by this following set, if it forms a frame for L2 and 0, then 1 or minus 1 must be the accumulation points for the point spectrum of T. Now, if we deal with a case when the index set J just have a single element, that is under our system under consideration becomes the set T and EM, where for a fixed M, EM was the orthonormal basis of the set L2, and we are taking a fixed element of that EM. Now, this theorem states that for a fixed M in J, the system T and EM, that is with a single sampling point, the system forms a frame for L2N. Then the point spectrum cannot have an accumulation point in the open interval -1 to 1, whereas it is properly contained in the open interval -1 to 1, but cannot have an accumulation point in this open interval. Now we deal with only the general bounded operators for both the finite and infinite for the infinite dimensional case, because here we give a characterization for the system T again to form a frame for H. The theorem states that the system T, which is T and Fi, where n belongs to n naught since we are in infinite dimension, then the system forms a frame for H if and only if the following three conditions hold. Firstly, the sequence Fi forms a Bessel sequence in H. Secondly, the operator T star is strongly stable, that is T and F norm tends to 0 as n tends to infinity. And thirdly, there should exist a bounded bijective operator phi on H, that is phi minus SF equals to T phi T star, where SF denotes the frame operator for the Bessel sequence Fi. Moreover, in this case, we see that phi turns out to be the frame operator for the system T. Now, in the following result, a class of acceptable operator, which is similar to contraction maps, that allows the system T to form a frame for H is given. So for that, we need to recall that contraction, a bounded operator T is said to be a contraction if norm of TF is less than norm F for each F. Now this, lastly, this theorem states that for any bounded operator T on H, there exists a Bessel sequence Fm in H such that the following two statements are equivalent. That is, the system T given by this set T and Fm, it forms a frame for H if and only if the operator T star is similar to a strongly stable contraction. Moreover, the set Fm is finite if and only if the rank of this operator I minus A star A is finite, which is again, this theorem is again giving a characterization for the system T to form a frame for H. Now, these are some references I have used. Thank you, everyone. Thank you for listening.
Thank you, Professor. Are there questions? Okay, thank you, Professor, for your
Thank you, sir. Thank you, sir. Thank you so much for giving me this opportunity. Thanks.
Okay, Professor Nikhil is now he is going to be the chairperson. Thank you, Professor Nikhil.
Thank you, Professor Johan. So the next speaker is Dr. Virender. So I think he's online. And Dr. Virender, if you are ready, you can share your slides and you can start.
Am I audible?
Yes, you are audible. I just like to say a few words about Dr. Virender. Dr. Virender is going to speak on operator representations of frames in Hilbert spaces. He is a professor in Delhi University. Dr. Virender, you can start with your talk.
Okay, thank you, Dr. Nikhil. And thank you, organizers, for giving me the opportunity to speak on operator representation of frames. Probably I may be excused because of the connectivity issues. The video is not so clear. Just let me share the screen and start with it. The earlier speaker has just spoken about the dynamical sampling in the quaternionic Hilbert spaces. The topic, the operator representation of frames is again very well connected with the dynamical sampling. So we can start with it. My screen is shared or not?
Yeah, yes, it is We can see the screen, yes.
Fine, thank you. Okay, so we would be talking about the operator representation of frames in Hilbert spaces. So this is the title of my talk. The content has been divided into 4 parts. The one is introduction. The second part is definitions. Obviously, we would be talking about the definitions in a running way or a simple one. Then we would be talking about some simple results which have already been proved in the concerning the operator representation of frames, or particularly in the dynamical sampling. And then it would be the references, the list of references which may be used for the further references. Okay, so let us start with the introduction. Okay, as we all know, the frames were introduced by the Finance Affair in 1952. In fact, they abstracted the fundamental notion of Dennis Gabor and then introduced the concept in L2R, the space of square integrable functions, square Lebesgue integrable functions. And later on, it was widely studied after a paper of Dersis and a book written by Young. Frames are generalization of bases in Hilbert and Banach spaces. We call them to be generalization of bases because they act like bases, so they give the representation to all the elements of the Hilbert space or maybe the Banach space, and they are generalized in that sense that they have the less condition imposed on them. Particularly, frames need not to be linearly independent, so they just behave like the bases but with a lesser condition on them. Recently, many variations or generalization of frames are being introduced by researchers over the time to explore more and more applications of the theory of frames. Introduction of new generalization give a wider range to frame in applications in the allied fields, particularly in geophysics, physics, electronics, communication, and nowadays it is in the imaging and compression, data storage, etc. Beside other applications, frames are used in sampling theory. When we say sampling theory, now over the last 20 years, it has been a very active area of research for many researchers, which is again very much associated with the dynamical sampling. The dynamical sampling is a new area of research in the harmonic analysis. So precisely, we would be looking for the reconstruction of a signal or a function using its nodes. We call them to be the sample. The topic of dynamical sampling was initially studied by Alrobi and Petrosyan. In sampling theory, every function which is a signal of the space is to be recovered from its samples. Obviously, we would be talking about what do we mean by samples and what type of representation we want a frame or maybe the collection to have. Stability condition is the extra condition which a frame possesses rather than the sample one. So, like a collection of sample can produce again the representation, but the representation may not be stable enough to process it. So the structure of frame is something which is having additional property to give the representation a stability, which is very used application part. So in dynamical sampling, every signal needs to be recovered in stable way by its samples. So it is just not about its recovery, but the recovery needs to be stable, or the representation has to be in such a way that we can talk about its convergence in terms of the norm, so that we are concerned about the recovery of the function in that manner. The dynamical sampling was initially used to analyze a linear diffusion heat equation, and later on it is spread to other areas as well. In fact, in the differential equation, such a problem is known as the inverse problem in differential equation. That is, we would be having the nodes and then we would be looking for the solution which satisfy the nodes. So the solution of the problem has potential application in other related fields where we can come up with the expectation, or we can come up with some sort of conclusion. So it is like medical imaging, weather forecasting, ecology, geosensing are some of the fields of applications of dynamical sampling. Because in all these areas we do have already the data which would act like a sample for us, and then we are going to make the signal, and then we can predict what is going to be in the near future for that particular signal. A lot of theoretical and foundational work has been done by various researchers recently. Once we just came to know of the potential the dynamical sampling is going to have for a given data and the potential use of it for the prediction. Now the problem is studied in self-invariant spaces also very recently. Okay, now let us come to some basic definitions, and then we give a couple of results to conclude our presentation. With a sequence Gj for a signal f, the collection of the sequence which is given in terms of the inner product f gi, this is referred as the sample of f with respect to the sequence gi. So when we would be talking about the reconstruction of f, then obviously we would be looking for the sample which is having of this form. Sorry. For a bounded operator T on a separable Hilbert space and X0 be an element of the Hilbert space, then again we would be looking for the frames which would be having the structure of T and X0, and this T and X0 is referred as system of iterations. So precisely varying the n, then we can reconstruct all the elements of the frames in a successful manner just by using the one operator T and an element X0, which is an element of the Hilbert space. The basic idea is to search for such operators with some elements of the space which can generate a frame fully. In other words, the search is for a class of frames which can be represented by an operator and with an element in terms of system of iterations. So once we can have this class of frames, then probably rather than making the whole class altogether, we can just use the operator and its iterations with X0, and we can recover all the elements of the frame fully. And then the frame can be used to recover every signal of the space. This is referred as operator representation of frames, which is a new and emerging direction in the theory of frames. So now we do have the two choices. The one is based on the sample available with us, we would be trying to recover the signal fully. Not only recover, but we would like to recover in a stable manner. The second one is we would be interested in characterizing all those frames which can be represented with the help of an operator and a single element, let us say X0. So again, just for the revision, a sequence of vectors f in H is a frame for H if there exist constants a and b, obviously positive constants, so that this inequality holds true for all f belonging to H. It follows from the definition that if f is a frame for H, then obviously the span of f is equal to H. If A is equal to B, then f is called a tight frame, and if A is equal to B is equal to 1, then f is called a partial frame or immobile tight frame. Also, if the upper half of the inequality is satisfied, then we say the sequence is a Bessel sequence with the bound B. A sequence of vectors f in H is a Ries basis for H with bound AB If F satisfies 2, that is the second condition over there in the previous definition. And for every scalar sequence Ck belonging to L2, we have this inequality A times of the summation Ck square less than equal to the norm of this, which is less than equal to B times of summation of Ck square. So this is true for all sequences in L2. So these are the two definitions which we use as a definition of frames and the Reed basis. The Reed bases are again in the same way, they are quite near to the basis with some additional properties, where the frames are the generalized basis. Now regarding the result, this is the first proposition. If we consider a frame, then we would be looking for the operator, or we would be looking for the conditions under which the frame can be represented using the operator or with the help of an operator. So this would be the frame having the operator representation. So consider a frame sequence Fk in Hilbert space H which span an infinite dimensional space. The following are equivalent. The first one is Fk is linearly independent. That means all the elements of the frames are linearly independent. The map Tfk is equal to Fk plus 1. If we define this map, then this map is well defined and extend to a linear and invertible operator T. The operator T would be from span Fk to span Fk, and in that affirmative case, the sequence Fk can be represented or would be having the operator representation. So just to have a sequence to have operator representation, we need to have the sequence to be linearly independent. So if there is a frame which is linearly independent, then for that particular frame there would be an operator which would be giving the operator representation to the frame. This is the second proposition. Consider a frame of the form Fk given by operator Tk with a element F0 for some bounded linear operator T. Obviously the T is from the span F to span F. Then the following holds, that is, the T is non-bounded below by 1. If T inverse is again an operator which is from span to span F, then this is bounded and T inverse would also be greater than equal to 1. So this is in the other sense we can say that if there is an operator T, then the inverse operator would act just in the same way and it would be bounded, it would be non-bounded below. If we consider a frame that is Fk, again it is of Tk form, that is having the operator representation with an operator T and with a element F0 where T belongs to BH, which is invertible, and if S is the frame operator, then we set F0 till that to be S inverse F0. Then S inverse Fk would be having again the operator representations, that is T star minus K F0 tilde. So using the frame operator inverse, we again get a dual as a frame again which is having the operator representation. So these are some of the basic results which talk about the existence of some frames which can be represented using the operator and an element, or the other way around. If we talk about the stability, then there is a result which is like this one. Assume that Fk is given by Tk F0, where T is a bounded linear operator. This is a frame for H. And let Gk be a sequence in H. Assume that there exists constant λ1, λ2 belonging to 0 to 1, such that this condition holds true for all finite sequences Ck. Then the sequence Gk is a frame for H. Furthermore, Gk can be represented with the help of an operator V, where V would be span of G to span G, and if T is bounded, then V is also bounded. So if two sequences are very close to each other, and if one is represented with the help of an operator, then other would be also represented with help of an operator, and both the operator would be behaving in the same way. Like if the first operator is bounded, then other would also be bounded. So these are the few results, because already the previous author has included more results, so I'm going to skip with that, and these are the references. Thank you.
Thank you, Dr. Virendra, for your very nice talk. Are there any questions? Are there any questions? I have one question. I mean, very obvious, because you have talked about
Yes,
a lot of motivation in your talk. I mean, for the people who have just started reading frame theory, how you can give the applications of the operator representation of frames over frames. I mean, how you will justify that the operator representation of frames has these applications? I mean,
right.
Think about.
If we talk about the frames, then it is collection, and precisely when we are dealing in infinite dimensional spaces, then the collection is infinite one. So we need to take care of each and every element, and when we would be reconstructing a vector or a signal, then we need to calculate these samples. But in case if a frame is represented with the help of an operator and using a single element of the space, then probably we get rid of remembering all the elements of the space or having the representation of all the elements altogether. With the help of just one operator and one element, just by making repeated iteration, we can calculate all the values altogether. So
Okay.
it would be more convenient, rather than to take care of all the elements or to memorize all the elements which we have included in the frame. It would be quite easy to just remember one operator which is behaving suitably with an element of the space, which can give the structure of the frame fully. I think that is more convenient for you.
Yeah. Thank you for your comments. And I also seen that recently, I mean, not very recently, but in 2022, one Iranian mathematician, he studied regarding this operator representation of frames. And I think that there is a lot of scope in this direction, and I wish you all the best.
Right.
Yeah.
Right. Thank you. I just would like to mention there, rather than using just one operator, now the researchers are combining the two or more of the operators all together, so that just combining two operators or more of the operators, they can have the similar representation. So that would be more generalized way. Rather than imposing many conditions on a single operator, they would be having two or more operator with the slightly lesser conditions, so that they can again come up with the same type of representation. So still they are working on it now.
Thank you for your answer. I think Professor Juan is having another question for you.
Yeah.
Yes, Professor, please go ahead.
Yes, excuse me for the question. In the previous talk, the condition to be a frame, so far I understood, is that I think it is a more restrictive condition than in the infinite dimensional case. So far I understand, in your case, which is an infinite dimensional space, you need only to that the spectrum of the operator is away from zero, whereas in the previous case the condition is that it does not have an accumulation point in the interval minus 1, 1. I don't well, I think it is only a commenter. I think that in the finite dimensional case, it is more restrictive than in the infinite dimensional case. That is only a commenter.
Okay.
Thank you.
Thank you very much. Thank you, Professor Juan. Thank you, Dr. Virender.
Thank you. Thank you.
I think Professor Jean Marvin is with us, and greetings to you, sir. How are you?
Yes. Do you hear me?
Yeah. You are clearly audible.
I am sorry because I did not receive any confirmation, so I did not know if things were happening or not.
It is okay, sir. You can proceed with your presentation.
Yes.
So
I share the screen. But there is somebody else sharing the screen.
So Professor Jean Marvin will be speaking on periodic solutions of generalized ordinary differential equations.
Okay, just a moment. I need to get my... Do you see the slides?
Not yet. No. Now your slides are displayed.
You see them?
Yes.
Okay.
Yeah, thank you.
So I can start.
Yes, sure. Thank you, sir.
Okay, I would like to first thank you for your kind invitation to speak in this conference. And I will report on some results on periodic solution of generalized ODEs. And it is a joint work with colleagues from the University of São Carlos in Brazil, Marcia Federson and Carol Mesquita. So I would like to dedicate the lecture to Stefan Schwabik and Jaroslav Kurzweil, who are really the most important people in generalized ordinary differential equations. Okay, so the founding paper of Jaroslav Kurzweil, as it is well known, appears in 1957, and his very last work was a book dedicated to generalized ODE. So he made many other things in mathematics, but really those generalized ordinary differential equations are among his most important contribution in mathematics. Okay, so as you know, the generalized ordinary differential equation come from having a new look to classical questions of ODEs. if we take an ordinary differential equation like this one, ordinary system, and we look for a Kara-Theodori solution, that means that we look for the equivalent integral equation as written here. And of course, in order that this equivalence is satisfied, the first condition is that this integral makes sense for all the function x we are considering. That means, for example, that we may find condition on f so that the composition here is integrable in the sense of Lebesgue. So if we define the indefinite integral with respect to the first variable of f as capital F of s and x, then of course when s is close to t in the considered interval, we can approximate this integral by assuming that x does not vary too much, so replacing x of sigma by x of t, and then this is just the difference of capital F at the point s and t. So if we consider a partition of the interval from 0 maybe to some tau smaller than capital T, then of course x tau minus x0, which can be written in this way as a telescopic sum, will be close to this sum, the sum of the capital F as Sj and x of Tj, and at Sj minus 1 and the same x. Okay, so if we now consider, as it is classical now, was classical in Riemann integral, but it's essential in Kurzweil approach, if we consider a pointed or p-partition of the interval, so a family of couples of points Tj and interval Sj minus 1 Sj, okay, with Tj in this interval, then, and if we define, we call gauge, a positive function over 0t, and we say that this p-partition is delta fine if essentially every interval Sj minus 1 Sj is contained in the ball center at Tj and with radius delta of Tj for all the value of j. When delta is constant, this is just essentially equivalent to the classical constant of p-partition with a given mesh considered in Riemann integral. Of course, the main difference with respect to the Riemann integral is that we cannot construct explicitly such delta fine p-partition, and a priori we are not even sure that they exist, but their existence for any arbitrary gauge is guaranteed by the so-called Cousin's lemma, which is essentially equivalent to the well-known Borel-Lebesgue covering lemma. So for each gauge, there is always a delta fine partition, so the type of Riemann sum we will consider do effectively exist. And the generalized Riemann integral as defined by Kurzweil in 1987 tells that if you give a function of two variables, u of s and t, we say that capital du, I will explain the origin of the notation later, du is Kurzweil integrable if we can find an element of Rn such that given any epsilon, you can find a gauge delta such that the difference between this type of generalized Riemann sum and J is in norm smaller than epsilon. So this is the sum associated to U, and you see that those sum contain, in fact, the differences of the function u at Sj and Sj minus 1 for a fixed state j, and this is the origin, this difference is the origin of the du in the notation of Kurzweil. And this j, if it exists, it's unique and is called the Kurzweil integral on du over t. It is quite easy to show that this integral has the elementary properties, linearity, additivity, and so on, of a usual integrable, and also that when you have integration over one interval, you have integration over the subinterval. And so we call K of 0 Trn the vector space of the K integrable function du over our interval. Of course, if you take for u a special case first, when u of ft is s multiplied by a function of t only, then you see that the corresponding Riemann sum are the classical sum for a Riemann integral. And in this case, it can be proved, it's not trivial at all, but that the Kurzweil integral is equivalent to the Danjois-Perron integral, so it's more general than Lebesgue. And if you take for u of ft separated variable, so the form g of s multiplied by f of t, then this sum, corresponding sum, looks like a Riemann sum for a Riemann-Stieltjes integral, and one can show, it was already done by Kurzweil, that this is the Kurzweil integral is equivalent to the Ward Stieltjes integral, so the generalization of the Stieltjes and Perron integral introduced by Ward in the 30s. And in particular, this integral may exist without G to be of bounded variation, and it contains many integrals of Stieltjes type. Having defined in this way a generalized integral, Kurzweil could define a generalized ODE, okay? And given a function capital F now of t and x, he says that x is a solution of the generalized ODE. Dx over d tau is df of sx. Notation is a little cumbersome, but I respect it. If the function of t and s defined by df of s of xt is Kurzweil integral, and if the corresponding integral equation here is satisfied. In such a definition, of course, because of the fact that here you don't have just an integral of a Kara-Theodori function, but you have a more generalized integral for which it is not at all guaranteed that this indefinite integral will be absolutely continuous. So a solution of a generalized ODE needs not to be absolutely continuous. That means, of course, that this notation, the left-hand member is purely symbolic. So writing this as a differential equation is purely symbolic, but it's helpful in order to generalize the classical's ODE to generalized ODE. And so what is effectively mathematically a generalized ODE is a special type of Volterra integral equation, where the integration in the Volterra integral equation is a Kurzweil integral. Okay. It's easy to see that because it's only the difference that occur in the Riemann sum, one can always assume without loss of generality that the function capital F will vanish for S equals 0, okay? And it's, of course, immediate to check also that if you take in this integral x as a constant, a, of course, then all the Riemann sum are just capital F of TA, and so, of course, the corresponding integral exists and is equal to capital F of TA. So, as just by the notation, the function f will play in some sense, will generalize in some sense the indefinite integral of small f in the classical theory of ODE. An important class for the study of generalized ODE is the class of regulated function, which I don't know if it was introduced before, but at least it was introduced in Bourbaki cours de mathématiques. And a function x is regulated, so if it has left and right limits at every point of the integral. So they don't need to be equal, of course. Again, it's a vector space. It's even a Banach space with the uniform norm. And the interest of this space is that it contains two important vector space of classical analysis, the function with bounded variations and the continuous functions. So their union is contained there. And those regulated function has a number of nice properties. They are uniform limits of step function, it's a characterization. They can have at most a countable number of discontinuities, and they have a continuous primitive in the sense of Bourbaki. That means the derivability can be missing on a countable set in the definition of the primitive. And what is interesting also is that one has an interesting, let's say, characterization of the relatively compact set in this space, so in some sense, some type of version for this space of Ascola-Arzeli theorem, which plays, of course, a big role in dealing with existence problem. Okay. For the class we will consider, we will make some regularity assumption, which were already considered by Kurzweil. This is not the only possibility you can do, but at least they allow sufficiently technically reasonable generalization of the ODEs. So those are assumptions, of course, on the function capital F, and so this measure the dependence with respect to T1, so it's some type of modulus of continuity. And here this describe the variation with respect to x and y. Okay. Script F will denote the set of the function capital F which satisfy this assumption. And so we will always assume that our function f, capital F satisfy is in this set. So we will not repeat in the theorems, we will not repeat explicitly those assumptions. What can be proved is that with f satisfying H1, any solution of the generalized ODE with x value in the corresponding ball R, will have bounded variation, and the variation will be estimated by the difference of h of r at t and 0. And also, when x is a regulated function and capital F satisfy H1 for all R, then the generalized integral of Kurzweil always exists. That means that the generalized ODE makes sense. Okay. Okay. Now, we will now be interested in the main topics of the talk, that mean the periodic solution of this generalized ODE, and like in the classical case, of course, a solution of the generalized ODE will be called T periodic. T is a fixed positive number if x of 0 is equal to x of t. Okay. Then we can define a map from the space of regulated function into itself, essentially by the following definition. M of x at a value tau, so the corresponding function here, is x of 0 minus the integral from tau to t in the Kurzweil sense of df. And this is defined for each tau in 0t. Okay. What is the interest of this map is that you can prove a very simple lemma. In fact, x is a t periodic solution of the generalized ODE star if and only if it is a fixed point of M, of script M. And the proof really takes a few lines. It consists of a series of equivalents. For example, I will read it in one sense. If you have a fixed point, so of this of M, so this is satisfies. And so when you take tau equal t, so this vanish, and so you have the periodicity condition. And when you take tau equals 0, you see that this cancel, and it remains that this integral is 0. And as this integral is 0, you can replace here this integral by the integral from 0 to tau, and you have all the condition to be a solution of the equation and to be periodic. Okay. With the lemma that compactness lemma that I described a few slides ago, then you can prove that M is continuous on this space, and it takes bounded set of G into relatively compact sets of T. So that means that M is what is called, script M is what is called completely continuous operator. So it's compact on all bounded set of G. Being a compact operator, or a completely continuous operator, it is clear that we can have in mind to prove the existence of fixed point for this operator, and that means existence for periodic solution of our generalized ODE by using Lorentz-Schauder degree argument. And Lorentz-Schauder degree is essentially a generalization to normed space, in particular to Banach spaces, of the Brouwer degree, which is defined for continuous maps in finite dimensional space. And I rapidly recalled that giving an open bounded set and a continuous function on the closure of D into E, a finite dimensional Banach space, and given a point Z which does not belong to the image by F of the boundary of D, one can define an integer which depends on F, on D, and Z. It's a relative integer called the Brouwer degree, which has the following properties. It's 1 if the F is identity and Z is in D, and 0 if Z is not in D bar. Remember, Z cannot be in this case in the boundary. So that's a normalization property. The existence property is that as soon as this degree is non-zero, Z must belong to the image of f of d. So that means the equation f of x equals z must have a solution in D. So proving that you have a solution follows from the fact that you prove that the degree is zero. It's not sufficient, but the implication goes in this sense. And very important to be able to compute this degree, or at least to show that it is not zero. In fact, this degree, this integer, will not change when you continuously deform f through a homotopy capital H, in such a way that during the deformation, the point z will never belong to the image of the boundary. So for each t of each lambda in the deformation. Okay, and if it is the case, the degree does not depend, does not change with lambda, is a constant. And a consequence of this is that this Brouwer degree is always invariant for small perturbation of the function, small in the sense of uniform norm. Generically, that means when the right-hand member makes sense, the degree is essentially an algebraic count of the number of counterpoints of Z in D by F. So by this relative algebraic count, I mean that those counter image will be counted by +1 if the determinant of if the Jacobian is positive, and -1 if the Jacobian is negative. Le Reich-Order degree, it's just a very clever extension of the Brouwer degree to an arbitrary real normed space, but not for all continuous map now, but for a special looking class of map, fortunately occurring often in the application, the so-called perturbation of identity. So the map that we consider must be of the form I minus or plus G, where G is a compact on all the bounded set or some bounded set of E, in the sense I have described before. And in this case, you can define an integer again, the Le Reich-Order degree, which has all the three properties I had mentioned for the Brouwer degree. With the only restriction that in the homotopy properties, in your deformation, of course, of the map, you deform only you keep the identity fixed and you deform only continuously the compact perturbation by remaining within compact perturbation and in such a way that, of course, your point Z again does not belong to the image of the boundary of D during the deformation. Okay. And when in fact your map G take and the point Z can remain in a finite dimensional subspace of E, then in fact the Brouwer degree, the Le-Rechaudder degree of identity minus G is the same as the Brouwer degree of the restriction of the map to F, which is then a map from F into F. And this is in fact the way in which the Le-Rechaudder degree is defined from the Brouwer degree by taking, in some sense, a larger and larger finite dimensional subspace. Okay, so we have this Le-Rechaudder degree, and then we can try to apply it to the existence of periodic solutions for our generalized ODEs. And the first result we can obtain is essentially an extension of the averaging method, so to generalize ordinary differential equations. Okay, and in fact, in this case, we will consider generalized differential equation where f, in fact, is of the form epsilon f, so epsilon being a parameter that we can take sufficiently small. So we are looking to some type of perturbation method. And the theorem we can prove in this case is very simple to state. So if you take the function capital F, this function here, for s equal t, and as a function of Rn, okay, and if you have an open bounded set of Rn such that the Brouwer degree of this map f of capital T x with respect to D and 0, z equals 0 here, is different from 0. So for some open bounded subset D of Rn, then there is a positive epsilon 0 such that when the absolute value of epsilon is smaller and non-zero, the problem, the generalized equation, has a T-periodic solution located in script D. So the existence of a periodic solution for small value of epsilon is therefore reduced to a finite dimensional problem. That means essentially showing that this finite dimensional map has Brouwer degree different from 0. And how do we prove this? One way to prove this is to define the map here, depending on the parameter epsilon, define capital H. We define it in the space G, that we have of a regulated function. So this is x0 minus the integral from 0 to t of d of 1 minus epsilon f minus the integral from tau to t of d of epsilon f. So it's a fixed point operator again, fixed point operator, which is a little more complicated than the one that we introduced previously, but which essentially is the same. And in fact, it's rather easy to show that when epsilon is non-zero, the fixed point of this operator H are essentially, they are the periodic solution of this differential equation. So for epsilon different from 0, in some sense, we can forget about this term in the operator. It does not really play any role. But for epsilon equals 0, it will be important because if we did not introduce this term here, when epsilon equals 0, the corresponding fixed point theorem would have all points would be fixed point and would be constant. And so we could not apply the Brouwer degree. So it's important to introduce this modification there. And so we have with this equivalence that when epsilon different from 0, finding a fixed point of this operator for epsilon small will provide us a periodic solution of this system. And to show that this operator has a fixed point, by remember the fact that the degree, Loray-Schauder degree and Brouwer degree remain constant for small perturbation of the map. So if we take epsilon equals 0, if we take epsilon equals 0, you see this term disappear. So the right-hand member of the fixed point operator belongs to Rn. This is a fixed value in Rn, and this is an integral, so this is in Rn. And so because of this, the Loray-Schauder degree at 0 is just the Brouwer degree of the restriction of the operator. And if you make explicitly the computation, you see, in fact, that this is the Brouwer degree of this integral with respect to the constant, because we are in Rn now. And so this is the Brouwer degree considered here. And it's non-zero. And as it is non-zero for epsilon equals 0, the invariance of degree for small perturbation will imply that it remains non-zero for epsilon different from 0. And then from the existence property of the Loray-Schauder degree, we have the conclusion that we have a fixed point of capital H, and so we have a periodic solution of this. Okay. We can deduce a special case of this theorem, which is reminiscent of the fundamental theorem of Bogoliubov for the periodic solution of ordinary differential system with a small parameter in Rn. And in fact, this generalization of the Bogoliubov theorem tells us that each time you find a 0 of capital F of t, we call it Ra star, but a 0 which is non-degenerate, so such that the corresponding Jacobian is non-zero, you can find a positive radius of a small ball and an epsilon star, such that this system has a t-periodic solution in the ball of radius R star in the space of regulated function for all epsilon smaller in absolute value than epsilon star and non-zero. Okay. The proof, in fact, you first use implicit function theorem to show that because of those conditions here, A star is the unique 0 in this ball. Okay, so this is the unique fixed point of h of 0 in the same ball, and hence by the property of Brouwer degree, we are in the generic case, if you like, and so the Lorentz order degree at 0, which is the Brouwer degree as computed on the previous slides, is the sign of the determinant of this, so it's plus or minus 1, and so it's non-zero. And again, we extend this non-zero property of the degree to small value of epsilon for the identity minus h, and then by the existence property, we have the result. And of course, in the special case of an ordinary differential system, this is exactly the extension of this Bogoliubov theorem with a completely different proof even in this case. Okay, and it is easy, I will not insist, it is easy to apply the theorem here to Riccati type equation, you generalized equation, which is essentially the case where the function capital F is a quadratic in X. And so one can make the discussion. And in particular, we can consider some equation which generalize the logistic equation. In this, I will not insist on those details. Okay. Now, from the previous case, we can in fact also obtain a global existence theorem of periodic solution. So a theorem which is not of perturbation type, and which has almost the same statement with one exception, but of course, this exception is the source of many problems when you want to apply it, but it's now for a system which has no small parameter, okay? Then we shall introduce, as it is usual by the application, in the application of Lorentz order degree, we shall introduce artificially a parameter in the equation, a homotopy parameter, which for lambda equals 0 should make, or small, should make the thing simpler, and for lambda equal 1 will reduce the problem to the one we are interested in, okay? And so the other assumption essentially will be that the function capital F of TA that we already considered previously does not vanish on the boundary of d tilde of its trace in Rn. What does it mean? It means that the space G, of course, contains the constant function, and so the constant functions are isomorphic to Rn because our x takes value in Rn, and so we can consider it as element. So this is the trace, if you want, of the boundary of d tilde on the constant function, that means on Rn. So this is supposed to be non-zero on the boundary. The Brouwer degree that we already had considered previously is non-zero. And what is the supplementary assumption is that by considering this family of equations for each lambda in 0 excluded to 1 included, we assume that this generalized ODE has no T-periodic solution on the boundary. So that means that we need a priori information for all the possible T-periodic solution of those equations, they have just to avoid the boundary of this set. This will happen, for example, if you can show that all the possible solutions are in a given ball, the same ball independent of lambda, because in this case, you just can take for d tilde a slightly larger ball, and so they will not be on the boundary of this slightly larger ball. Okay, so that's the so-called method of a priori bound. Okay. And to prove, to prove this theorem, we proceed like in our proof of the averaging method, except that we replace lambda epsilon by lambda here to insist on the fact that lambda now will have to go until 1, okay? We again have the equivalence between the operator introduced in this proof and the periodic problem here, and by the homotopy invariance, which holds because of all our assumptions. Then the degree of the fixed point problem for 1, which corresponds to this differential equation, to the periodic solution of this generalized differential equation, will be essentially the same as the Lagrange order degree at lambda equals 0, and we have seen that this was just this Brouwer degree here. And so all the conditions to apply the Lagrange order existence property of Lagrange order degree are satisfied. So of course, the difficulty in the application, but also the exciting point in the application, will be to check essentially this condition, those a priori, to find those a priori estimate, which were not needed where we were only interested in solution for small lambda here or small epsilon. Okay. It's very difficult to find explicit condition for this theorem in the frame of generalized ordinary differential equations, or except trivial example, of course, can always be constructed, but it's more interesting to see special cases of those generalized ODE, and there are several ones, and in particular, as Schwabik has shown it, the generalized ODE contains the so-called impulsive differential equation, the IDEs. And what is an impulsive differential equation is essentially given a priori a finite sequence of points in 0t. You define the difference, the jump, at the point te of the function x being the right limit minus the left limit. And we can take a subspace or our space of regulated function in such a way that they are left continuous. And so in this case, this will be the value at ti. It's not diminishing generality. So now, given some function I continues from Rn to Rn, and a Karateodori function small f, the impulsive differential equation is an equation which is an ordinary Karateodori equation at points t different from ti, and such that the jump at ti is controlled by the value of x at ti. Okay. So this is what is called an impulsive equation, and you can show that such an impulsive equation is equivalent finally to an integral equation of this form, where H, capital H here, is the Heaviside continuous function, 0 for t smaller than d, and 1 for t strictly greater than d, the left continuous version of this. Okay. And now, in fact, what we show is that, or what Schwabik has shown, is that this can be also written as a generalized ODE. We make on the function small f a number of assumptions, essentially in order that our equivalent generalized ODE will satisfy the famous assumption H1 of the beginning of the tool, of course, and by solution, of course, of the problem, it's standard to assume that X is absolutely continuous on each sub-interval here, satisfies the differential equation for t different from ti, and satisfy the jump condition at the ti. Okay. And by defining, which in a very natural way, capital F by this expression, which occurred in our equivalence, we can show that this function satisfies our assumption H1, and the Kurzweil integral is just the expression occurring in the integral form of the IDE. Okay. So we have reduced the problem to a generalized ODE. You can find details in the nice book by Schwabik, you know, okay? And then we can just translate now our theorems in the setting, the special case of the periodic solution of impulsive differential equation, and this is the result you obtain. So again, you have the a priori estimate condition for the family of equation here with a lambda in 0, 1 artificially introduced. The mapping capital F is now explicited by this, and the corresponding degree has to be non-zero. Okay, and so in this case, we have a periodic solution. And I can give you an example to show that in this situation, really, the a priori estimate can be obtained. You can consider here a scalar equation, a scalar impulsive differential equation, which is written in this way, with E an absolutely continuous function satisfying the one periodic solution, and we look for a one periodic solution. And this is the characteristic function of irrational number, so you have quite a discontinuous coefficient there. And you can prove that the a priori estimate holds for a sufficiently large ball, okay, which depend on the data of the equation. And then when you compute the function capital F of 1, you can show that it has a unique zero in the trace of this ball in R, in the constant function, with a positive derivative partial, and so the degree will be +1, and so this function has a one periodic solution. So this is a small example. Other problems, of course, can be considered for generalized ODE and has been considered. And the applications, of course, also of the generalized ODE go beyond what I have done here. and they cover some functional differential equations, so delay differential equation, measure differential equations, a differential equation on time scales, and some question also in topological dynamics are really given a new light in the framework of generalized ODE. And you can, for example, read the nice recent book of Bonotto, Fedorson, and Mesquita. They are the editor. It's a collection of chapters written by a number of authors, to see really the power of the generalized ODEs. Our paper, where most of this talk is based on, was published in the Bulletin des Sciences Mathématiques, and those are the reference to the book and paper of Kurzweil. Of course, Kurzweil has many other papers on the topics too, covering other questions, including also the other side of averaging method, which is averaging on large interval. Here I have concentrated on a topic Kurzweil has not considered, which is generalizing the averaging method for periodic solution problem. Okay, so I think I spoke enough, and I thank you for your kind attention.
Thank you, Professor Marvin, for your insightful talk on generalized ordinary differential equations. And at the end, I've seen that you have given some of the other problems and applications from functional differential equation to topological dynamics. That's really impressive. Thank you very much. I would like to ask the other participants if they have any questions. They can ask Professor Marvin.
Hello, Professor. Hello, Professor.
Yes.
Yeah, first of all, I like to congratulate your presentation was so good. I was enjoying, and your area was also very good. Sir, here you have presented Creswell approach. So I'm also working in this area. I like to know why you have not taken hand-stroke approach.
I'm sorry, but the sound is very bad and seems to have been interrupted now. No?
Yeah. Am I audible?
No. We have problem with the sound.
My question was, sir. My question was.
Yes, please go ahead.
Yeah, my question was, you have taken the Creswell approach. Then what will be the limitation if we take the hand-stroke approach, only hand-stroke approach? What might be the limitation? What might be the problem?
I really cannot understand your question because of the sound. So can you repeat it?
Sir, okay, I'll mail you, sir. I'll mail you later.
Can I try to help?
Yeah.
This is Marcia.
Can you read?
Hi, ma'am.
Can you read it in the chat, please?
Yeah, probably the chat would be nice. But he's asking what would be different if you would use Hansstock's approach instead of Kurzweil's approach. But in that sense, I would ask him, what does he mean by Hansstock approach?
Actually, I mean by Hansstock approach means in the sense of primitive, actually. Creswell took the definition in the sense of Riemann sum. Then Hansstock, he took the definition in the sense of primitive of the function. He was not directly took the Riemann sum.
Yes. But so hello, Marcia.
Hello. Were you able to get it?
Well, I don't see the difference between the Hansstock integral and the Kurzweil integral in this setting here. Of course, Hansstock has defined integration in a very general setting, but I think that his generalization of the case of a one-dimensional, of the integral of a one-dimensional scalar or vector function do not really cover or do not give something different in the case of the integral considered here by Hansstock, and in some sense they are essentially integrals of interval function of one variable, you know. But
I believe
I don't
that
think that Hansstock could help in this respect because it's the same.
But I believe that Kurzweil's approach helps us to make the link between the what you said, the Volterra integral equation, and a differential equation in a wide sense. I think this would be a good contribution that makes it very clear for us. There's a chapter in Schwabig's book where he manages to say what is a Hansstock solution to
okay.
Yeah.
I understand better what you mean. Okay, so you know what Hansstock has tried to do is in some sense to see how we can go beyond Kara-Theodori solution by replacing in this setting Lebesgue integration by Perron, and so by a Hansstock-Kurzweil integral.
Oh man!
But of course, Schwabig has shown that it does not really go much beyond the Kara-Theodori situation.
Differential equation.
But of course, well, there is still work to do in this direction.
Yeah, thank you, sir.
I would like to ask you, Jean, if you assumed that the capital F is a periodic function. Did you? I don't remember. It's just that I don't remember that.
Excuse me?
Did you assume that the capital F is periodic?
No, you don't need it, because I consider here the periodic function problem, periodic solution problem. You can always consider it in two ways, either as a boundary value problem, x of 0 equal x of t, and you don't look what happens outside this interval, or you assume a t periodic dependence on the independent variable in your equation, and then you look for a solution defined on the whole line, and which has the usual, which takes the same value after adding t, when your equation is periodic with respect to t, so when the value at 0 and at t are equal in the equation there, then of course the two problems are equivalent. You can extend your periodic solution on 0t, capital T, as a periodic solution on the real line. But when it's not the case, you lose the equivalence. So the two problems are close, but not always equivalent.
And I also was checking on our book that we were dealing with the averaging problem when inside the capital F, you have the S divided by epsilon, and the epsilon outside and the epsilon inside also. And somehow we were able to relate both equations. So I believe there is something else to add to this averaging study that you're doing. I think the more can be done in the way that you put the epsilon outside plus an epsilon
and
under
the
S. Under the S.
But we have the linearity of the integral, so it really does not matter, I think. Huh?
No, but inside the capital F.
Yeah, excuse me. Okay. You can add, of course, dependence on epsilon in F2. I just did not put it, not to make the notation too complicated, but it's just for the presentation. Yeah. Everything works the same with an epsilon, a continuous dependent epsilon inside of the capital F. Yes, you're right. Yeah.
Great. It was nice seeing you here.
It's nice to hear you.
Hello, Jean. It's Milan.
Yes.
I would ask about this extension of Bogolyubov theorem.
Yes.
Is it contained in the paper? To my opinion,
no. It is not. I have just written it now, but it's not contained in the paper. But I can send you the.
Of course, I would enjoy it.
Yeah, sure. But it's not. No. It's a little extra.
Okay. Thanks.
Thank you, Professor Marvin. And are there any other questions? If there is no other question, then let us thank the speaker. Thanks again, sir.
Okay.
So the next speaker with us is Dr. Hemant Kalita, Dr. Hemant Kalita from VIT Bhopal University, Madhya Pradesh, India. And he will be speaking on convergence of new McShane integral on complete metric measure space. Dr. Kalita, you can share your screen.
Yes. My share. So my screen is visible, sir.
Yes, your screen is visible.
But I'm opening this one, but it is still showing in the recent.
are not appearing, only the folder is
Yeah.
visible.
Acha, 1 minute, sir. I have not seen my video on. Some issues are coming in my desktop, sir.
You can open the PDF file and then you can share. Then automatically it will take to the screen where the file is open. So that will not be a problem. You can try this other way. You can first open your PDF file and then you can choose the option of sharing the screen, and then you will be looking at few options. One of them would be where you will be able to see that slides.
No, I have opened actually. Just a minute, sir.
Yeah, no problem.
Sharing the screen. I like to present a small topic on convergence of mu-Maxent integral on complete measure space. And myself, Hemanto Kalita, and I'm from GIT Bhopal University. So, sir, next slide. Okay. In this presentation, I like to show the abstract introduction preliminaries and construction, how we construct a mu-Maxent integral on a complete metric space, and several convergence of mu-Maxent integral and some references. Okay. Basically, in the abstract, in this talk, basically the monotone convergence theorem, mu-Maxent equi-integrability, and uniform strong Lawsian condition are discussed on a complete metric space, and with a Radon measure mu with a family of cell that satisfy the Vitali covering theorem with respect to mu. Finally, we prove convergence of mu-Maxent integrable sequence of function based on the concept of equi-integrability is equivalent to the Vitali convergence theorem. Okay, if we observe, Lebesgue integral is regarded as an official or standard integral in the discipline of mathematics by a large portion of mathematicians. A significant amount of measure theory is needed to understand the Lebesgue integral. The abstract concept of measure theory makes Lebesgue integral complicated. In the late 1960s, Maxent defined a Riemann type integral, proof that it is identical to the Lebesgue integral. Being a Riemann type, it is more user-friendly to work than Lebesgue integral. Measure and sigma algebra are also excluded from this integral. Maxent integral had undergone several extensions. Gordon introduced and developed the properties of Maxent integral for the case of function has a value in a Banach space. Z. Karau introduced mu-Hansprock causal integral in his doctoral thesis in 2023 and 2024. This is our base paper. Based on his work, recently I myself proved mu-Maxent integral is equivalent to Lebesgue integral. Motivation behind this work is J. Criswell and S. Sobik's work, Maxent equi-integrability and Vitali convergence theorem, that was published in 2003. So their work, in that work, the work of Criswell of the Maxent equi-integrability and Vitali convergence theorem motivated us to investigate several convergence theorem of mu-Maxent integrable sequence of function based on the concept of equi-integrability that is equivalent to the Vitali convergence theorem. Okay, now coming to Radon measure. Recall the Radon measure when X M mu is in a measure space. Given an outer measure mu on X, a subset E of X is called a mu measurable in the sense of Kara-Theodori if mu of A equal to mu of A intersection E plus mu of A set minus E for each A is a subset of X. Suppose U is a Borel sigma algebra of X, recall that a measure mu is called Radon measure if mu is a Borel measure with the following condition. First is mu k less than infinity for every compact set K subset of X. Number two, mu of V is sup of mu K where K is a subset of V, K is compact for every open set, V is a subset of X. And third, mu of A equal to infinity, infimum of mu of V, such that A is a subset of V and V is open for every A subset of X. Let lambda be a signed measure defined on the sigma algebra of mu measurable subset of X, then lambda is absolutely continuous with respect to mu if mu of E is 0 implies this mu mod of mu, it should be actually mod of mu E equal to 0 for each mu measurable subset E of X, and we denote this lambda less than mu. In the entire work, we consider mu is a non-atomic radon measure. This met BBD is a family of non-empty closed subset of X. For E subset of X, we denote indicator function, diameter, interior, and boundary of E by psi E, diameter of E, E to the power E naught, then del E respectively. Throughout this work, we denote dXE is the distance from a point X to E, where E is a subset of X, as we mentioned. Now, coming to mu cell, we recall that if Q1, Q2 are a subset of D that are non-overlapping, if interior of Q1 and Q2 are disjoint, a finite collection Q1, Q2 .qm of the pairwise non-overlapping element of D is a divisor of D if union I from 1 to m Qi equal to Q. We consider G is a subfamily of D, then G is a fine cover of E if infimum of diameter Q, where Q belongs in G, and X is the element of Q equal to 0 for each X in E. We call D is a mu Vitali family if for each subset E of X and each subfamily Z of D that is a fine cover of E, there exists a countable system Q1, Q2 Qj of pairwise non-overlapping element of Z such that mu of set minus union of Qj equal to 0. We consider F be mu Vitali family. We say F is a family of mu cell if satisfy the following axiom. Axiom are given Q in F and a constant delta greater than 0, there exists a division Q1, Q2 Qm of Q such that diameter of Qi less than the constant delta for I from 1 to m. Number 2, given AQ belongs in F and A is a subset of Q, there exists a division Q1, Q2 Qm of Q such that A equal to some Q1. And third condition, mu of boundary of Q equal to 0, measure of the boundary 0 for each Q in F. Now we recall Vitali-Carathéory theorem. This is based for the Lebesgue integral. Let F be real function defined on a cell Q. If F is Lebesgue integrable on Q with respect to mu and epsilon greater than 0, then there exist functions G1, G2 on Q such that G1 less than equal to F less than equal to G2. G1 is an upper semi-continuous and bounded above. G2 is lower semi-continuous and bounded below. Then Lebesgue integral over Q, G2 minus G1 is less than epsilon. Okay, now coming to the construction of mu Maxwell integral in regard to the radon measure. So we recall a gauge on a set Q is any positive real function nu defined on Q. We have formulated a few definitions here. Let a Q belongs in F, then E subset of Q and nu be a gauge on Q. A collection XIQi I from 1 to M of finite order pair of point and cell is said to be a free take partition of Q if Q1, Q2, Qm, this set is a divisor of Q and Xi belongs in Q for I equal to 1 to M. A free partial partition on Q if the set Q1 Q2 Qm is a subsystem of division of Q and Xi in Q for I from 1 to M. A nu find that collection is a nu find if diameter of Qi less than nu Xi for I from 1 to M. E-tag if the points x1, x2, x3 xm belongs to the set E. The following Cauchy's type lemma address the existence of our nu find free partition for a given cell Q. The lemma we construct here, if nu is a gauge on Q, then there exists a nu find free partition on Q. I have omitted the proof. We define the Riemann sum as follows. Let f from Q to R be a given function and matrix P be any partition of Q in F. We define the Riemann sum as SFB equals to sum from I to M fxi mu Q I. And this Riemann sum is not hard to see, is well defined. With the help of this Riemann sum, we defined a mu-Maxent integral as follows. A function f from Q to R is mu-Maxent integrable on a cell Q with respect to mu if there exists a real number I such that for is epsilon greater than 0, there exists a gauge nu on Q such that the Riemann sum minus L absolute value is less than epsilon whenever this matrix B P is a free take partition of Q that is nu find. And throughout the work we write I is equal to integration over Q f d mu is the collection of mu-Maxent integrable on Q or by mu m Q. Mu mq is the collection of all mu-Maxent integrable on Q. And uniqueness is not hard to see. It is clear that a mu-Maxent integrable function is mu Hansproch-Casual integrable on a cell Q and the integral are equal. We have found several properties for mu-Maxent integrable. Linearity property hold, and if f is a mu-Maxent integrable greater than equal to 0 positive function for each x in Q, then integration over Q f d mu is greater than 0. And lastly, we found fg are mu-Maxent integrable. And if f less than equal, if greater than equal to z for each x in Q, then over integration on Q f d mu greater than equal to integration over Q z d mu. Next, we found Cauchy type criteria also satisfied by mu-Maxent integral. A function f Q to R is mu-Maxent integrable if and only for each epsilon greater than 0 there exists a gauge nu on Q such that Riemann sum on a partition B1 minus remain sum over partition B2 under modulus less than epsilon for each fair new find partition, this metfrac P1 and metfrac P2 of Q. The following theorem shows that mu-Maxent integrability of F on a set implies its mu-Maxent integrability on each subcell of Q. Theorem is that if F is a mu-Maxent integrable and A is a subcell of Q, then F is mu-Maxent integrable and integration over A F d mu equal to integration over Q F characteristic function on A d mu. Next, we shall show that if F is mu-Maxent integrable, then mod of F is also mu-Maxent integrable on Q. This property is not hold for mu-Maxent integrable that we found on the thesis Z. Karatos in his doctoral thesis. He has mentioned that this property is not valid for mu and stroke Criswell. To show this, we need the following lemma. Lemma is shown here. Let F from Q to R be mu-Maxent integrable on Q. Given epsilon greater than 0, let nu be a positive function on Q. If this set and these are free take partition that are nu find, then the summation from I to 1 to n, summation j equal to 1 to m, mod of fxi minus fyj, mu of ij intersection kj is less than epsilon. With the help of this lemma, next we have seen that if f Q to R is a mu-Maxent integrable on Q, then mod of F is also mu-Maxent integrable on Q. Next, we have seen Sek-Hansbrook lemma also satisfy for mu-Maxent integral. To do that, we define additive function like below. Let pi from F to R be a function. We say that pi is an additive function of cell. If for is Q in F and for each division Q1, Q2, Qn of Q, pi of Q equal to sum I from 1 to n pi of Qi. Next, we have construct a proposition. Let F from Q to R be mu-Maxent integrable function on Q. If Q1, Q2, Qn is a division of Q, then F belongs in mu-Maxent integral over Q1 intersection mu-Maxent integral over Q2 intersection mu-Maxent integral of Qn, and this integration value equal to sum from I equal to 1 to n integration over Qi f d mu.
Dr. Hemant, please conclude. Your time is almost over.
Okay. Sir, many are there. Anyway, okay, I will not come to the conversion part. Let me see up to the relationship of Lebesgue integral. We have seen in the next theorem that if f is Lebesgue integrable, then it is mu-Maxent integrable, and conversely, we can show that the function, if it is a mu-Maxent integrable, then it is Lebesgue integrable also. And based on that, we have in the next session actually several mu convergent lemma theorem were there. Since time is and I have already taken many time, so I like to conclude my presentation. And thank you very much for your attention, and I like to apologize. I took several time and unable to show my slide myself.
Thank you, Dr. Kalita. Are there any questions to the speaker? If there are no questions, so let us thank the speaker. Thank you, Dr. Kalita, for your presentation.
Yes, sir.
So from now onwards, Professor Juan would chair the session. Professor Juan, are you here? Professor Mendoza?
Hello, I am here now.
Yeah, thank you, Professor.
¿Qué pasó? Hi, Nikhil.
Okay. Professor Marcia, are you ready?
¿No va Carolina?
Perdón. Excuse me.
Va Caro. Primero va Caro,
Please,
luego va el profesor Milan y luego
Please, Maria Carolina Mesquita. Please go ahead.
Okay. So let's see here. One minute. So, can you see my presentation? Professor
Yes.
Juan? Yes. First of all, good afternoon or good morning, everyone. It's a pleasure to be here. First of all, I'd like to thank Professor Juan and Professor Javier for this kind invitation. It's really very nice to meet all of you again. It's very nice to meet. So let's start. The title of my talk is Bifurcation of Periodic Solutions to Generalized Ordinary Differential Equations. This is a joint work with Professor Milan Tvirj. So here in this work, we are consider a boundary value problem for this generalized ODE in blue, where capital F here is Kurzweil integral, and we proved a result that ensures a necessary condition for the existence of a bifurcation point of this boundary value problem, okay? This research is started with this paper here. This is a joint work with Professors Marcia Federson and Professor Jean Mawan. Here in this work, we proved a result that ensures a sufficient condition for the existence of a bifurcation point for this problem, for the same problem here, the boundary value problem. But, Milan, are you talking? Sorry. I think not. We proved
the screen by Carol.
Hi, Milan. Sorry, I can't hear you properly.
Wrong.
I can hear you properly, Milan.
Somebody spoke.
The previous
Sorry, Mila. I can hear you properly. I don't know. Let's see here.
Oh.
Mila?
But
let me
well,
open.
well,
Sorry, Milan, I cannot hear you properly.
yeah, but up to now, still the previous presentation was on the screen, and your sound was bad.
Oh.
You were talking, but the presentation was the previous one.
Oh, I will try to share. I will try to share again. There is a problem with my presentation, with my voice, or with the sound.
Share with your presentation is not seen on the screen.
Okay. I will try to share again. Thanks for letting me know. So let's try again.
Excuse me, Professor Milan. I think it was a problem from your computer.
Let me try again.
Why.
Professor Wang, it's possible to see my slides?
No.
Milan, it's possible to see my slides now?
No.
No.
You should share the screen, but the organizers should also to.
I will ask the technical.
Professor Juan, it's possible to see my slides? Can you see my slides? No.
Right now, no.
In this moment, no.
It's a pity. Let me try to go out of the meeting and try to go into again. Let me try that.
But at least now your sound is good.
Oh, thank God. At least that, Milan. Let me try to go out of this meeting and go into again. So let's 1 minute. So let's see if can I share properly my presentation.
Yes.
Yes?
Yes.
Oh, that's nice, Marcia. Now it's possible, no?
Yes.
Thanks for letting me know. Thanks. So let's start again. The title of my work is Bifurcation of Periodic Solutions to Generalize Ordinary Differential Equations. This is a joint work with Professor Milan Tivij. Here in this work, we consider a boundary value problem for this generalized ODE in blue, where capital F is Kurzweil integral, and we proved a result that ensures a necessary condition for the existence of a bifurcation point of this problem here. This research is started with this paper here. This is a joint work with Professors Marcia Federson and Professor Jean Mawan. In this work, we proved a result that ensures a sufficient condition for the existence of a bifurcation point for this problem, for the same problem here. But here in this paper, we worked with bifurcation points with respect to the trivial solution. But here in this present work, we are working with bifurcation points with respect to any solution, okay? So this talk will be divided in two parts. I'm going to talk about bifurcation problems to generalized ODEs, and Milan after me will talk about the same results, but on bifurcation, but in the framework of measured differential equations, okay? So let's start talking about generalized ODEs. Let's define a generalized ODE using its solution. Here we need to consider omega an open subset of Rn and f a function like that. A function x from 0t to Rn is a solution of this generalized ODE if the range of x belongs to omega, and moreover, this integral equality here is satisfied. Note that here, in the right-hand side of this equation, we have the Kurzweil integral, as Mawan defined it on his lecture very well. As Mawan said, here, it's important to mention that D here, capital D here, does not mean differentiability. Here is just a notation for the Kurzweil integral. I will not go into the details of the formal definition of Kurzweil integral because Mawan explained it us very well. But it's important to keep in mind that the Kurzweil integral is more general than the Riemann integral and the Lebesgue integral. And moreover, the Kurzweil integral deals very well with functions with many jumps, I mean, many points of discontinuity and a high oscillation. Because of these facts, the Kurzweil integral is a very nice tool to work. It's a very powerful tool to work. Now, I'm going to introduce a specific class of functions.
¿Presentar a Marcia? Sí, por eso.
Professor Juan?
¿Cuántas faltan? Pues el níquel ya me dejó aquí.
Oh, it remains a lot of slides, unfortunately.
De hecho, Milan me mandó un mensaje que no.
No. Yes, we have more 11 slides.
Excuse me, no problem. Excuse me, it was my fault. Excuse me.
No problem. Let's continue. No problem, Professor. Here, I'm going to introduce a specific class of functions as Mawan defined it on his lecture as well. Here, we suppose that there exists a no decreasing function weight and a continuous and decreasing function omega, such that omega in 0 is equal to 0. Here we have the capital F in blue is the set of all functions that satisfies these two inequalities here. Note that the first inequality involves the function weight and the second inequality involves both the function weight and omega. This type of definition will be very important here in this work. Now I'm going to introduce the space that we will work here. Let's do that. Here we have a function from 0t to Rn. It's called regulated if the lateral limits here exist. Then we denote by G in blue, capital G here in blue, is the space of regulated functions with the usual supreme norm. This space will be that we will work here. Now I'm going to introduce, we are able to introduce our bifurcation problem. In order to do that, we consider T a positive number and this periodic boundary value problem. And here we need to assume two conditions. The first one says that capital F here belongs to the class F for each lambda, where lambda here is an open subset of the real line. Remember that here, F belongs to this class means exactly this definition here. And moreover, we need to assume that lambda x0 in lambda times G is the space of regulated functions, is a solution of this problem, boundary value problem here for every lambda that you consider. Remember that our goal here is to prove a result that ensures a necessary condition for the existence of a bifurcation point of this problem here. In order to do that, let's introduce a specific operator. So here we need to consider an open ball centered at x0 in the space of regulated functions. Then we define the operator phi from this domain into the space of regulated functions. We define phi by that in blue, by that equation in blue. And of course, here we need to assume if x belongs to this ball, the range of x needs to be in this open set here in Rn for every t that you consider in this interval 0t. Here we have an important correspondence result, very similar that Mawan presented on his lecture, very similar approach. This correspondence result says for each lambda, there exists a correspondence between the fixed points of this equation involving this operator and the solutions of this boundary value problem. And it's easy to see that because if you have here, phi is this operator here, I wrote here, it here. Then if x is a fixed point, we have that this part is equal x and s. And then it's possible to see that x is a solution. And if you take here s equals 0, this integral in the right-hand side disappears. Then you have exactly that, x0 is equal xt. Then we have that x is a solution for the boundary value problem. Because of this correspondence, instead of looking for bifurcation points for this boundary value problem, we will look for bifurcation points for this equation involving this operator phi, and this correspondence simplifies our work. This is very useful to us here in this work. Now, let's introduce the definition of bifurcation point. A couple lambda 0 x0 in G in lambda times G is called a bifurcation point of this equation here, involving the operator phi. If every neighborhood that you take of this interval if every neighborhood that you take of this point, lambda 0 x0, it's always possible to find another solution, lambda x, such that x is different from lambda 0. Then this is the definition of bifurcation point. For every neighborhood, it's possible of this point, it's always possible to find another solution, of course, different from x0. So this is that existence theorem that I mentioned in the beginning of my lecture that ensures the existence result that says, if we assume 1A2, remember that 1A2 is that F belongs to this class, and here we have this point is a solution for the boundary value problem. And moreover, we need to assume the condition 3. What says the condition 3? There exists a non-decreasing function such that this inequality here in blue is satisfied. Moreover, if we have that this interval here, lambda 1 star, lambda 2 star, is contained in lambda such that this number here, this is a notation for Lattice-Chalder index, and the Lattice-Chalder index is defined by Lattice-Chalder degree, as Mawan explained very well about topological degree. But here, the Lattice-Chalder index is defined by Lattice-Chalder degree, but in this case, it is calculated in the neighborhood of the solution 0, but 0 needs to be an isolated fixed point of these operators here, phi and lambda 1 star and phi and lambda 2 star. If we have that the Lattice-Chalder index, these numbers here are different on the extremes of this interval here, lambda 1 star, lambda 2 star, then there exists a lambda 0 in this interval such that lambda 0, 0 is a bifurcation point of this equation involving the operator. But because of that correspondence, we have a bifurcation point. We have that lambda 0, 0 is a bifurcation point of the boundary value problem. But how about a result that ensures a necessary condition? So let's see further. To prove a result on that ensures a necessary conditions, we need to assume 3 hypotheses. Let's see them. Here we assume C1 for every pair here, lambda t. F, the function capital F is continuously differentiable with respect to the second variable, I mean omega. Remember that omega is an open set of Rn. Here C2 says we need to assume that the derivative of F with respect to the second variable needs to be that class. Remember that definition of class is exactly that as I explained it in the beginning, but instead of using capital F here, we are using now the derivative of F with respect to the second variable, but it's exactly the same definition. Then the third one says there exists a non-decreasing function such that this inequality is satisfied, but this condition C3 is very similar to condition 3, but instead of using capital F, we are using in this case the derivative of F with respect to the X, to the second variable, but this type of condition is very similar to 3. So now, to prove our main result, we need a characterization of the derivative of this operator phi, as I mentioned here, with respect to the second variable, okay? So if we assume that just C1 and C2 hold here, C1 and C2, the first 2 conditions, then it's possible to present a characterization for this derivative of this operator with respect to the second variable. And then this characterization is given by that in blue, by this equation here, for all z in the space of regulated functions. Now I'm able to introduce our main result. Note that here we need to suppose all the hypotheses, the previous hypothesis, and if the operator identity minus the derivative of phi with respect to the second variable applied at this point, lambda 0 x 0 is an isomorphism, then there exists a delta positive number such that all points here lambda x in this neighborhood of this point lambda 0 x 0, all point in this neighborhood is not a bifurcation point of this equation. I mean, if all point here is not a bifurcation point of this equation because of this that correspondence. We have that all point here in this neighborhood is not a bifurcation point of the boundary value problem. To prove this result, we used the implicit function theorem for Banach space, because here we are dealing with spaces in infinite dimension. Okay, and the last theorem ensures a necessary condition for the existence of a bifurcation point, and says, here again, we need to assume all the previous hypotheses. If lambda 0 x 0 is a bifurcation point of this equation, then there exists a Q in the space. Remember, G is the space of regulated functions, such that this linear equation here has no solution in the space of regulated functions. And the homogeneous equation here, like that, has at least one non-trivial solution in G. To prove this result, we used the previous theorem here, plus a Fredon alternative, okay, to prove this result. So here we have the references. Some of the results that I presented here are in this paper with Professor Milan, and also some of the results on bifurcation are contained in this paper with Professor Federson and Mawan. And here we have Mawan's book and Schwab's book. So thank you very much for your attention. Thank you. That's it.
Are there questions? I have a question, Carolina.
Right.
This setting is very general, but I think that, well, what about to use just the Henson-Kurzweil integral instead of such a, I think it is a very general integral. What did you present?
Okay.
What will be the difference?
For me, thanks for the question, Professor Wong. For me, the Kurzweil integral and the Henstock-Kurzweil integral, there is no difference. I think the approach is the same. The integral, to me, as far as I know, if you use the Henstock-Kurzweil integral, is the same here. It's the same approach that, for me, these integrals are the same. I don't know if I got your question very well.
I understand that this integral gives not a continuous function sometimes. I understand.
Could you repeat, please, Professor Wang?
This integral gives not a continuous function. So far, you understood.
Yes. We can integrate using this. Let me come back here. Here we can integrate functions that are not continuous, are not differentiable. It's much general, if I understood your question very properly.
I understand that if you use Henstock-Kurzweil integral here, you get a continuous function. Is that possible? Or it is not?
I think not. To my opinion, if the Henstock-Kurzweil integral here is the same, it's the same definition. It's exactly the same.
Okay. Maybe later I ask you.
Okay,
I
Professor.
am skipping something. Thank
you. Thank you very much for your questions.
Okay, and any more questions?
Yes.
Can you hear me?
Hi,
Yes,
Carol. Nice to hear you. I
nice
have
to
no
hear
question.
you.
I have no question, but just it was very nice result and a very nice talk. Congratulations.
Thank you, Professor Jean. It's very nice to meet you again, even online. It's a really pleasure.
Hi, can you hear me?
Yes, I can hear
Yeah.
you, Milan.
Because I have from some reason signs that I'm muted, but it's strange. I have just comment, Carol. I have a
Okay,
suspicion that that condition with the two different values of the degree could be thanks to the Bogoliubov theorems, extension of Bogoliubov theorems mentioned by Jean, can be replaced by something more natural, difference of two determinants. We will see.
Oh, okay, you think that the approach used by Professor Jean can use it here
This
in
crucial condition. This one.
This one can be changed by that Malone
Just
presented.
some difference of two determinants, but I believe.
Oh, I hope so. We can change. Oh, we can try, no, to check. Thanks, Milan. Thanks for your remark. I like it very much of that. I like it very much from that result from Jean. I didn't see that approach for such equations. It's very interesting.
So you are welcome, and you had a nice talk.
Oh, thanks, Milan. Thanks for everything. It's very nice to meet you again, even online, and Professor Jean and all of you. It's very nice. Thanks for the opportunity.
Okay, thank you for your talk.
Thank you, Professor Juan. Thank you very much. It's very nice to see you again.
Thank you. Likewise.
So let's see here, stop sharing.
Are you ready, Professor Milan?
I cannot. I hope that I am not muted. And now I would like to share the screen. I have a strange question whether I would want to allow to Cerebro to see my screen, but the possibility to allow is dead. I have it download. I don't know.
Milan, what about if you do the same as Carol, just going out and in again and try to share again?
Yes, I'm afraid that I have to do it. So, sorry.
Dr. Miller, I'm not listening to you.
Yeah, do you hear me?
Yes.
But still I did not succeed to share the room, share the screen. Once more. It's something strange I see, but not my screen. What do you see?
We see some sharing of your screen, but maybe the room itself, not a PDF or something.
No, either me.
Is your PDF open?
Yes, it's open.
Maybe you have the
I have here, you are screen sharing.
Yes, you are, because we are seeing your screen, but not the PDF. Maybe when you are going to share, you have to choose a file.
You must
I cannot get my.
you must not share your screen. And choose your file, and then you must share your screen.
Yeah, but
you go to your PDF now.
Stop sharing, please.
Stop share.
Then now you choose your file. Please choose your file, and then.
But where I will choose it? I have it open now.
Yes, and now you please share your screen.
No, that's what I'm doing. Share screen once more. Now to choose the window. I see. I know. Do you see it?
Yes. Perfect.
Sorry for. So my talk is closely related to the talks of Jean Maven and Carol Mesquita. It's in fact continuation of the talk by Carol, but now I'm concentrated about the special case of generalized differential equations, namely nonlinear distributional differential equations. Well, here is the introduction, but I don't need to repeat it because it was already done by Jean Maven, both Carol Mesquita. These are repeating about the regulated functions and functions of bounded variation. Our topic is a periodic problem for distributional or equivalently the measured differential equation of the form this one, where the basic assumptions are clear. Some of them, T is positive number. The functions f and g are acting on some subset of omega of Rn. They have values in Rn. And in addition, function f has a parameter lambda, which is from some open set capital lambda. And this function u, which is here, is supposed to be to have a bounded variation and to be left continuous on the half open interval 0t and to be extended to the left and to the right as a constant. Solution x is a short solution and it's an n vector valued function. And now what is more important, by capital D we denote the distributional derivatives of the functions which are following. So dx and du are distributional derivatives of x and u respectively. And the crucial term is this one, which stands for the distributional product of function. This dot means the distributional product, and it will be explained later. Now, so everybody who touched the theory of distributions know what are these test functions. Test functions are smooth functions which are zero outside of the interval 0t, and topology on this space of test function is given by uniform convergence of all derivatives excepting the zero derivative. And distributions are considered as linear continuous functions on this space. So we are in the Schwarz sense. And it's not surprising that the star is denoted by the star is denoted the space of distributions on the finite interval 0t. As usual, if f is a distribution and phi is a test function, then by this classical sign, we denote the value of the functional f on phi. And there is some relation with the real functions. For example, if f is a Lebesgue integrable, then the corresponding distribution can be represented as in the integral form. So if phi is test function, then the corresponding functional f is given by this integral. And it is also known that the zero element of the space of distributions is measurable function vanishing almost everywhere on the interval 0t. And in particular, if f is a regulated function which is left continuous on this half open interval, then f is a zero in a zero distribution if and only if the function f is zero everywhere. And well, for distribution, the symbol df stands for the distributional derivative, which is defined by means of some form of the integration by parts theorem. So is the distribution is the functional which gives to given a test function f this expression which is obtained as the minus f applied to the derivative of phi. This is also well known. Recall that if f has above absolute, f is absolutely continuous, then the distributional derivative and the usual derivative coincide. And if the derivative of f is zero, derivative of f is zero if and only if f is Lebesgue integrable, and the function and is constant almost everywhere on the interval 0t. Well, to go back to our equation, we say that x is a solution of this equation if and only if f has a bounded variation, is left continuous, x has a bounded variation and is left continuous, and its values, all its values lies in that capital omega on which this function f and g are defined. And the second condition is crucial, the distributional product of the composition of g and x with the distributional derivative of u has a sense, and this distributional equation is satisfied for all test function phi, where again this is symbol for the composition. Well, the main problem is that there is no general definition of a product in the space of distributions. Well, what is known, the trivial example is that f is a test function and g is distributions, and we can define the product of f and g in this trivial way. So we shift g into the part where the test functions appear because of g is a test function, so the product of two test functions is again test function. So this is trivial example. Also, if f and g are such functions that their product is in L1, then we can represent the distributional product of f and g by means of the Lebesgue integral, or in fact f times g times the test function phi. But for our purposes, of course, this is not enough, and we introduce the following definition. Whenever the Kurzweil-Stiltes integral of g with respect to u exists, then the distributional product of g and the derivative of u is the derivative of some function h. This function h is an indefinite integral of g with respect to u. This definition has a good sense. It's well defined whenever u has a bounded variation and g is regulated. And only one disadvantage appears. The distributional derivative of the product f times f and g does not satisfy the usual formula. It's in addition to what we expect, derivative f times g plus f times derivative g, there are some two additional terms where this g tilde and f tilde are there are some jumps of g tilde and f tilde, and precisely defined in this way. The similar situation appear when you deal with the Stiltes derivatives of functions. So go back to our equation. It's we can expect that this equation, our equation, will be equivalent to the integral form where we integrate everything. And here this we are integrating from 0 to t, and here is the value x of t. This includes the periodic conditions. What is known, sometimes they consider the equations with the Lebesgue integral, and Lebesgue Stiltes. So the first integral is the Lebesgue one in general. But here they have usually the Lebesgue Stiltes integral over the half open interval, and they have here the sign measure generated by the function u. But in our book with Giselle Monteiro and Antonin Slavík, we succeeded to prove that whenever this Lebesgue Stiltes integral exists, then of course, the Kurzweil-Stiltes integral exists also when they have both they have the same value. In the opposite is not true. If only Lebesgue-Stiltes integral, if the Kurzweil integral exists, then it's not necessary that the Lebesgue-Stiltes integral exists. So, well, first preparatory result says that under our main assumption A1 and these assumptions are natural assumptions about the function f. So f is supposed to be Kara-Theodori for any parameter lambda. G is continuous in the first variable, and furthermore there is some function n m with the index u such that it's integrable with respect to the variation of u, and it's in fact it's an integrable majorant of the function g. Let me emphasize now that usual works in usual works dealing with the Merger equations, they assume that u is a monotone function, which is not needed here, but this is replaced by this the integrability of the function m with respect to the indefinite variation of the measure u. So if this is true, then any solution of the integral equation is has a bounded variation and is left continuous. So I will skip the sketch, and it follows that this our original equation written in the differential sense is equivalent with this integral equation under our assumptions. Well, I skip the proof. Now, of course, these measure equations are special cases of the equations of generalized differential equations mentioned before by Carol, and in particular, thanks to all the results by Stefan Schwabik, under our assumptions, we can show that for any parameter lambda, we have a functions h and omega depending on lambda, having the good properties such that this indefinite integral of our functions, this expression, belongs to that class F, which was described in the talks by Jean Maven and Carol Mesquita. It means that these inequalities are true. And moreover, the integral, Kurzweil integral with this symbol df is the same as our integrals with which we are now working. So here is recalled what you saw in the talk by Jean Maven, and this is just to illustrate the meaning of the class capital F. So this gives the possibility to prove the existence of the solution of the initial value problem. And well, now we met what are the definition of bifurcation points. I will recall the definition for the generalized differential equations. We say that if x0 is a solution of this problem for all lambda, and if rho is such that whenever we take a function in the raw neighborhood or closed raw neighborhood of this x0. So this is understood in the sense of the uniform topology on the space of regulated functions. Then all values xt belongs to the set omega on which the function f is living. So when we say that this couple lambda zero x0 is a bifurcation point of our problem, if every its neighborhood in a lambda times the regulated functions contains solution lambda x such that x is different from x0. And again, recall that this problem can be represented in the operator as the problem of the fixed point of the some operator. Here it's denoted by phi tilde. If we add assumptions denoted here as b1 tilde, then well, maybe this I can skip. This you already saw. Only I will mention the existence results, the sufficiency results by Fedderson, Magan, and Carol Mesquita, which says that if we find some points lambda 1 stars, lambda 2 star, such that the corresponding degree are different, then there is lambda 0 in the interval lambda 1 star, lambda 2 star, such that lambda 0 x0 is a bifurcation point. But our main concern is well, as an application, we can get the similar result for our measure differential equation. It's natural to expect that this is true. Well, but as here is an example which was taken from the paper by those three authors. If we consider the impulsive problem of this kind, where b and c are Lebesgue integrable functions and integral of b does not vanish, and we consider such equation that we can see that x0 is a solution for all lambda. Linearization at x0 is the following, and there are it's possible to find lambda 0 down and lambda 0 up, such that this condition is satisfied, and that means that 0, 0 is the bifurcation point. On the other hand, our main concern is to find the necessary conditions, and the necessary conditions are given here. It's based on the basic results which could be found for example in the book by Aman. So if we assume that the operator phi tilde has a derivative with respect to x, which is continuous on lambda times the closure of this neighborhood of x0 with the radius rho, assume that something like that exists, and if identity minus this derivative is an isomorphism of regulated functions onto regulated functions, then the couple lambda 0 x0 is not a bifurcation point of our equation. Well, it follows from the abstract implicit function theorem. So the question is to find in a
Professor Milan, have you finished? Or there is a problem?
I think he has been disconnected, and now
Yes.
he's trying again.
Yes, I think there is a problem with the internet. And maybe he has not noted that he's out.
No, he's trying, you see?
Okay. We can wait. Let me ask if we have a problem here, or it is a problem of him. They are telling me that Professor Milan lost the connection. So yes, we can wait a little. Please, Professor Milan, can you finish your talk? Or do you want to continue, please? Professor Milan? Yes. Sí, entiendo. Professor Milan, can you connect the song in your computer?
No se escucha.
Oh, okay, I understand. We wait a little more to see Professor Milan can connect.
Problem again with sharing the room. I don't understand what happened.
Yes, no problem, Professor Milan. Can you choose your file and share your screen, please, once again?
But I do not have an opportunity when I there is something where I could choose what I want to see, but my screen is not here.
Stop sharing, please.
What?
Stop sharing your screen, please. The red one, the red. Okay, then please choose your file, and once again share your screen.
Yeah, but there is no choice to choose my only whole screen, but my screen is not here. My screen is not available.
Below at the bottom of the screen,
there is a share screen. When I push it, then I have seen it's in Czech, but choose the window or screen. And if I open this, I see the main fourth online seminar, and then nothing. If I choose this, I see something. Nothing. Not my PDF.
Please open your file, please.
But it's not possible.
Maybe it's because I can see. Maybe it's available to me and not for Milan. Is it possible to be that?
I will share my screen and to see if we have a problem. Are you seeing my screen?
Yes.
Yes, okay. It is the same. It is not a problem from here.
But I don't see. Now I can. I hope that it will be.
Yes, it is okay.
It will appear again, but
Please,
I don't know.
Repeat some slides.
What was the moment when you lost me?
I think a slide before this one, please.
2 slides.
Yes, it is okay.
Yes. So here is repeating the result by Carol that if the identity minus derivative of the operator representing the problem is an isomorphism on the space of regulated function, then this couple lambda 0 if 0 cannot be bifurcation point of the given problem. And then this result can be applied, of course, on our problem in measures. Now here it's something where it's shown that how is the derivative defined, and unfortunately I skipped on. This is important for us under the general the assumptions, and in addition, if we assume about the derivative of f with respect to x and g with respect to x, similar conditions which we assume about the function f and g. So derivative of f is a Kara-Teodori function and g is continuous, and there is some majorant. It has a majorant, some majorant, which is integrable with respect to the indefinite variation of the function u. And then the derivative of phi of that operator representing the problem can be explicitly expressed in this way. So as one can assume that it's the integral where is a derivative of f with respect to x. So it's linear operator, so acting on some function z, and similarly it's in the second part. Well, if we denote this is in fact the matrix. If we denote it, it depends on lambda. If we denote it as A with the index L, or B is similarly the derivative of G with respect to X, then one can see that this identity minus phi, derivative of phi applied on Z has a zero. So Z is a solution of this linear operator equation if and only if Z is the solution of this linear equation, which is in fact the generalized differential equation, or it can be written in the form of linear equation with measure. And then it's easy to, or relatively easy to determine whether, in fact, what is important now, if this equation has only trivial solution, then the derivative of phi is isomorphism on G, and so this is a negative result about the fact that whether lambda 0, x0 can be bifurcation point. And at the end, I show the example starting with the fact that such function 2 plus cosine t to the third power is solves for all lambda such a parameterized impulsive problem. It's the two periodic boundary value problem, and so here we have some integral form, but they will be specialized. It's this is a system of two equations. X is a equation the unknown x is a vector with two terms. The first one is u, and the second one is the derivative of u. So you can see that the origin was the equation of the second order. F is such a function where what is essential is this term, which is taken from the Libau-Welvlis pumping model, which in origin is the singular periodic boundary value problem of the second order. And here this term represents some possible jumps, and the jump takes place in the point pi, and R is given in this. This is some polynomial in cosines. And the corresponding linearization of this problem is the second order 2 pi periodic problem with where Q can be computed, and it can be verified using some results obtained by Robert Huckel and Pedro Torres, that this linear problem has only the trivial solution, which means that this couple x0 and 0 cannot be bifurcation point of for this problem. So that's similarly one can obtain for the example mentioned before, for the existence of the bifurcation point, that for some other values than z lambda 0, we do not have the bifurcation. but I did not mention here. And this is all. And I apologize for not completely well prepared talk, because of I just this afternoon I learned that the conference starts today, and even that my talk is scheduled for today. And at that time I was just leaving hospital after some routine observation. So nevertheless, I hope that it was not time lose for you. Thank you very much. Yeah. Is there anybody?
Thank you very much.
Did you hear me?
Yes.
Did you hear me?
Thank you very much, Professor Milan.
I'm.
Are there questions? Excuse me for this question, Professor Milan. When is it possible that this setting can be in some way equivalent to the other presentations, to the other formalisms that they have presented before?
It's closely related to the talks by Jean Maven and Carol Mesquita. It's a continuation of the talk by Carol Mesquita. It's concerning one very special case when we can verify some general conditions in a more explicit way.
You mean is it a special case of the?
Yes, in fact, it's a special case, but you know, for some special cases, you can get more detailed results and more explicit conditions when the assumptions are satisfied than the most general cases. So it's.
And the distributional integral is involved here, or it is not?
No,
from Professor Eric Talvila.
No. This is not. I don't know whether the distributional derivative. In fact, distributional derivative for when you integrate the functions regulated with respect to boundary functions of boundary variation or vice versa are the same as the Kurzweil-Stites integrals, and more general situation are not possible.
Okay, thank you.
You are welcome.
More question? Thank you for your talk, Professor Milan. I am beginning to understand. Hope so. Are you ready, Professor Pedersen? Okay, please.
It's nice to be here to see you all again. I also was not sure if the conference was going on because I had no email about confirmation of day and time. So it was just because Carol wrote me yesterday night, and then
Yes, that was my fault. Please excuse me.
It's okay. So what I'm going to share with you, it's part of what we are doing. This is part of the PhD thesis of Antonio Veloso, and Rodolfo Collegari is a co-advisor with me. So since we have been able to define what would be generalized stochastic equations, we have been interested in stochastic equations. But here I'm not going to talk about Kurzweil-related integrals or anything like that. I'm just going to talk about the known Ito-Henstock integral, which was developed and still is being developed by the group in Singapore. Those are academic descendants of Rolf Henstock. And by the way, they are writing a book on Ito-Henstock integration. I think this is gonna be a very nice book for all of us. So I'm going to give you here some preliminary notation for us to know what's going on. We are going to consider, let me pick up this, Hilbert spaces, because, well, we are always thinking about Hilbert spaces as the counter domain of our operators, because we want to think of the most general possibilities of problems, which are problems appearing in quantum mechanics. So for instance, when you think of Fock spaces, those involve Hilbert spaces. And for instance, here you could say that it's not necessary to do so, but since we are already in this environment of functions taking values in Hilbert spaces, so we are producing the same environment to get more and more information about this. This is mainly related to populations, but I believe that maybe we can think of applications related to many particles. I would say a population of particles. So maybe this could help also in problems coming from physics. So we get a orthonormal basis for Hilbert space U, and then LUV is the space of bounded linear operators from U to V, and this HS here is the space of Hilbert-Schmidt operators, which are bounded linear operators such that this sum here is finite. This is used in physics, and we'll see later that we can think of a space of random variables which are in L2, but this can be extended to LP. I'll mention that. So we are thinking of a probability space, a degenerate interval, and a filtering probability space, which you have some increasing sequences concerning the time t as the time passes by, then f t1 is included in f t2. And here we are considering these operators in LU because we want to consider a more general notion of Brownian motions or linear processes. But we could think of regular Brownian motions. The only difference here is on the third requirement that we have this Q here. In regular Brownian motions, we have independence of increments, continuity of paths, and Gaussian distribution with means 0 and variance t minus s simply. So we are going to denote by L2, this straight L2, the space of random variables with norm, this norm here. So we could think of P here and 1 over P here. And this round L2, this round L here, would be the space of stochastic processes which are adapted to that filtering probability space. So the norm here is going to be the integral of the expectation of the random variables, which is then this we can write it this way or this way. So straight L2 stands for the random variables and round L2 for the stochastic processes, and a stochastic process is formed by many random variables. Also, this now is some particular difficulties I have with the notation that people from probability use. So for me, it's not always clear which is the domain and which is the counter domain on the way they write things. So we have been struggling to write down the operators, where they are coming from, where they are going to, very carefully, so that we from analysis can understand in a very nice way these operators. Usually they skip some information, having in mind by their culture that it's implied within the context. But coming from another environment, which is not probability theory, I have been struggling with the notation, and so we have been trying to define spaces. So for instance, this is one notation we are using for the space of all operators from omega to Hilbert space V. And then F here takes values which would be the times in the interval AB. So for each time t, ft would be a random variable, but the collection of all ft's would be a stochastic process. So this is what we are thinking about. And now I will go to the definition of the Ito-Hastock integral, which I think is very nice. And we have these delta fine belated partial divisions. Okay, what is that? We have a gauge of an interval AB, which is a function taking no negative values, so the zero can be a value here in the counter domain, and a finite collection of point interval pairs, like here you have intervals and here points. This could be closed to here or not. We have different definitions, and they don't matter concerning the results. So this could be a closed interval here. And we say that this collection of point interval pairs is delta fine if these subintervals are contained here in this ball. So it is fine to one side, let's say, concerning the classic idea that we have for delta fine division coming from Kurzweil and Henstock integration theories. We say that it's belated because of the endpoint being the left endpoint. I mean, the tag being the left endpoint, and a partial division because the sum of all subintervals doesn't need to equal the whole interval AB. Okay, but at a certain point, the group from Singapore realized that there was it was necessary to have another number, a positive number, for the fineness of the partitions. And so they defined what would be a delta eta fine belated partial division. Okay, again, we have the pairs interval and here a tag. The tag is being here the left endpoint of the interval. And now the interval AB, where we have by Vitali covering lemma that this number eta exists where we fail to cover the interval by a set of Lebesgue measure eta. So when this happens, we have delta eta fine belated partial division. I believe that the introduction of this eta was coming because without it, I found myself unable to prove Cousin lemma for this integral. So I think that at a certain point, I can point out that from 2012 on, the Singapore group started to add this eta in this definition for the shrinking of the partitions. So what we have then is that the Ito-Henstock notion of integrability for a stochastic process F would be the following. You need that the Riemann sum, and this is a Riemann-Stieltjes sum, where these B's here are connected with the Brownian motion. So they are the random variables of the Brownian motion. You need that this sum converges in a sense to some value I. But as we are dealing with probabilities and stochastic processes, this convergence is with respect to the expectation. So we need the expectation of this difference here to be smaller than epsilon. If this happens, then we call this I here the Ito-Henstock integral of f with respect to the Brownian motion B. And this here means that this equality is being fulfilled almost everywhere in omega. Okay, and we have the fact that Ito integrability implies Ito-Henstock integrability. So every function which is Ito integrable is also Ito-Henstock integrable. And if we consider such a stochastic process with initial, such a stochastic equation with initial condition given like this, and we think of its integral form, then we have this blue equation here. When you have a stochastic process for which every random variable xt satisfies this equation, then we say that the stochastic process x formed by all random variables xt is a solution of the stochastic differential equation. So coming exactly from the theory of stochastic equations, they deal already, even for the Ito integral, they deal with integral forms of differential equations. That's their kind of mild solution, I would say. Okay, an interesting stochastic equation appearing in population dynamic is this one here, this part here, and this part here. We can generalize for that one, that previous one. And they usually use in the integral form the Ito integral. We are going to change it for Ito-Henstock integral. So our equation is more general. For this equation, we know the following. Let me skip a little bit here and then I'll come back. For that equation, we know that we have Kara-Teodori and Lipschitz-Stadt conditions for the indefinite integrals, or for the integrals, let's say the integrals involved in the integral equation. But what we need here is that the expectation of these integrals fulfills some conditions. So these hypotheses are coming from Henstock's hypothesis used in his book that Professor Jean showed, his books on generalized ODEs. The same kind of thing, but here, because we are dealing with stochastic process, now we have to add these expectations here. Otherwise, it's the same idea. Okay, so having this being satisfied, we have the existence of a unique solution, and then we can have maximum interval of existence, and then probably in some circumstances, global solution. And okay, now we have to consider some properties of population models, which are extinction, persistence, and permanence. Well, you can have permanence of a population if it doesn't blow up. If it does, if it increases forever, then this can generate a future extinction of the population because they can fight for food within themselves. So we have this little difference between permanence and persistence of a solution of a population. So for persistence, we have more that these limits being above zero. Extinction, of course, the limit is going to zero, and then the population is going to be extinct. And for permanence, we need it to be below an M. Then it is kind of controlled in some sense, and it doesn't grow forever. And in this way, the population continues forever. Okay, so it's clear then that permanence implies persistence, and we have lots of implications. These are some of them. And okay, under the hypothesis of existence of a global solution, and under the hypothesis that the stochastic integrals exist, we were able to establish condition for the solution of general solution of a stochastic differential equation to be strongly persistent. In fact, we were dealing with a more general equation. We added a perturbation of this equation by a Levy noise, and because of that, we are dealing with a Poisson measure and a Poisson integral, which is a sum. And even though we get strong persistence of the solution. Okay, again, this means that probably in the future, it may happen that the population may grow forever and then have problems with food. So, and these are the first results that are coming, and the results are for a very general equation, and not as the people who are working in population dynamics through stochastic equations are doing, because they are dealing with one equation and then another and then another and then another. And the way Antonio was able to manage it was to consider them all as particular cases of this general problem that he's dealing with, plus perturbation by Levy noise. And this perturbation by Levy noise is very interesting because they involve this Cadillac modification or Caglad modification, which resembles us very much of regulated functions, either continues to the right side or continues to the left side, but they resemble of these. So these Levy choices, these Levy processes are processed with jumps. And these jumps, they, in our mind, they have these very easy equivalence with regulated functions in the ordinary case, the deterministic case. So this is what I wanted to share with you for today.
Okay, thank you, Professor Marcia. Are there questions? I have a question. Is this model can be applied for COVID?
For what?
For COVID
I think
evolution?
so. Yes, I think so. I think so. Any kind of population, viruses, and so on. Yes.
Okay. Thank you.
In this case, you are looking for extinction. So.
And what is the prediction of your model in this
So
case?
more or less that you need, since prediction is exactly the complementary of persistence, then you need the opposite. Then you get extinction. You need that the limit goes to 0 and then it extincts, the population is extinct.
But what does it mean that? What is the condition for extinction?
Well, for here I didn't put it because we need that the limit of the functions which are involved in our stochastic equations, the f and the sigma, they remain above 0. So probably it's just so that when you send them to 0, it's going to be extinct, just naturally like that.
I do not understand what will be what will be the condition. Not
here when you ask this f and this sigma, the limit of some mean with respect to the integral, it's 1/t, the integral of a to t of this, and then the norm of this, the limit of this as t goes to infinity to go to 0, then you have extinction.
Yes, but I mean, maybe it is too difficult to answer the question, but what does it mean in reality? Do you
in
have
reality,
an idea?
that the population is going to be extinct. So for yes. COVID, you want the viruses to be extinct. So you want the population to disappear.
Yes, I understand that. But what will be the condition in reality in real world? What could be the necessary condition so that it happens? Do you have an idea of that?
Yes, the norm of 1/t of the integral of 0 to t. This, I want the limit as t goes to infinity to be equal to 0. Then this is going to be extinct. But then for special cases, for certain populations where you know what f means and what sigma means, then you can reduce the problem and do like Milan and Carol were doing, getting a special case and then dealing with a really special case and giving more accurate information on the population. Like if I take the food of the population, then they are going to go to 0. But a second problem would be, I want it to go immediately to 0. I want it to be extinct. So this is one thing that we are dealing in a group of women, and we are thinking of a population of I wouldn't know the name in English. The red blood cells for this disease called sickle cell. With the disease is the following: inside the cell there's a polymerization, and then the format of the red cell, instead of a round thing, becomes like a sick thing, like a sick cell, like a C. And then this causes pain for people who have this kind of disease. And this disease is typical of descendants from Spain, descendants from Italy, but mostly descendants from African groups. So Black people can have this. So in our group, we have two women. These are mathematicians working in this, and they are Black, and they are interested in this. And what we want here is the extinction of these cells, that they are killed somehow with some medicine, or that they are recovered somehow with the medicine. So in this case, we are going to deal with a very special equation, not with a general F or a general sigma. We are dealing with a very special equation and dealing with this polymerization thing.
Okay.
Yeah, and then the conditions are specified to this, and that they are stronger in the sense that they have very specific meaning.
Yes, that's quite nice. Thank you. Are there more questions? Well, if there are no more questions, then I think we have already finished the day. Finished the day, I think. Yes. So I wish you, thank you all. It was very nice. There were very nice talks of all of you. I thank you very much your participation, and we hope that we can see next time.
Bye-bye.
Nice to meet you, Professor Magwin.
Thank you. Bye-bye.
Bye-bye.
Bye, sir.
Bye.